Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the Adoption Engineering team at Google Cloud, and today we're going to talk about adding arrays to our Outcomes section in YARA-L. In this video, we're going to cover two aggregation functions that are often used with strings in the Outcomes section, array and array distinct. Remember, it's important to understand that when working with multiple events in a rule, that all outcome variables that contain UDM fields must have an aggregation associated with them. The syntax we'll be using is the outcome variable equals array or array distinct, followed by the UDM field or a placeholder variable inside parentheses. Finally, it's worth mentioning that arrays are truncated after 25 elements, but when using array underscore distinct, all deduplication will take place before the truncation occurs. To me, this makes array distinct my go-to aggregation for strings. Now that you know a little bit more about arrays in outcomes, let's revisit our password spray rule and refine it further by adding additional outcome variables to it. If you recall, our current rule identifies Microsoft user login events with a block action, as you can see in the event section. We're grouping our detections by the match variable hostname over a 30-minute window, and we have a condition that says we need to have more than 10 unique user IDs within that window to trigger. When we introduced count and count distinct, we added these outcome variables and our two constants to the rule. In our test rule, we can see that we have counts of the number of events that were part of the detection as well as the count of the unique user IDs attempted. But what if we wanted to see a listing of the user IDs? We could expand the detection to see the user IDs in each event, but if we're going to use this information elsewhere, it would be nice to have a listing. Let's add outcome variables for both array and array distinct to our rule. Notice how we can use UDM fields or placeholder variables in our outcomes. When we run our test rule and add our two new columns, we can see that the array distinct variable contains a listing of 13 user IDs, which align to our distinct count of 13. Our array, on the other hand, contains 25 user IDs that have duplicate IDs in them. Clearly, with all of the events rolled up into this detection, we don't have all the user IDs shown here. Array is a fine function to have, but in most scenarios, you will likely find that array distinct is what you want to use because it distills the relevant users, assets, or other field values down and removes duplicates. Much like we did with the single event rule for Who Am I, let's take a quick look at a version of this rule with outcome variables built out, including the distinct array of user IDs. If we view this in our alert graph, we can see each one of these user IDs in the rule and its association to the detection. Array and array distinct are just two of the aggregate functions that can be used in the outcome section. Remember that all events values must be aggregated in rules that contain multiple values. To use these aggregate functions, they follow a common syntax. The outcome variable equals the aggregate function like array or array distinct, followed by parentheses with either the UDM event field with the event variable or the placeholder variable inside of it. Finally, 25 elements is the maximum stored in an array. I found that the array distinct is my go-to aggregation because it performs a deduplication prior to applying that truncation, so I can see just unique values in my outcome variables. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the Adoption Engineering team at Google Cloud, and today we are going to build a multi-event rule using a sliding window in our match statement. In previous videos, we have built multi-event rules with a match condition called a hop window. The hop window is the default windowing used for multi-event rules in Chronicle. While this works in many cases, there are occasions when a sliding window is needed, and that is what we are going to talk about today. In a sliding window, we're going to identify an event that opens the window and holds it open for a period of time before or after that event for the detection. The syntax in the match section remains basically the same, but the keywords before or after, followed by the event variable that opens the window, are appended to the original match condition. Providing a sliding window provides additional flexibility for detection use cases, but there is a performance cost to be mindful of. Nothing else about multi-event rules that has been previously discussed changes. Sliding windows just impact the data matched in the time frame identified. To illustrate how a sliding window works and doesn't work, here's a visual that our engineering team created. Our match condition is looking for values within a 5-minute window after the event denoted as A occurs. The window is held open once that A event occurs, and after 5 minutes it is closed. As previously mentioned, we can also use the before keyword to look for events that occur before the A event as well. The catch with sliding windows appears when there are a number of A events. When our criteria to open that match window is very broad, like process launch, user login, network connection, DNS query, we can end up with a tremendous amount of windows being held open. In these cases, it's better to use the default hop window and add in the ordering to use the event times and the greater than less than operators within the rule. However, in our example, we'll walk through an example that would be a decent fit for a sliding window. Our example to highlight the use of sliding windows is to build a detection around the extraction of the ntds.dit file. For those not familiar with the ntds.dit file, this is where Active Directory data is stored, including users and password hashes. It isn't readily available, but there are some different utilities and methods to gain access to it. For our example, we're going to monitor for process launches of 2 of those methods, and then monitor for the file creation of the ntds.dit file using our sliding window. Let's start by naming our rule ntds.dit T1003003, which is the MITRE ATT&CK technique and subtechnique ID, and add it in the meta section. In the events section, let's start by laying out the events that we want to monitor for. We have process launch events for both NTDS-util and VSS-admin utilities, and to provide a little more precision, we have added some additional options to those utilities that might be seen in the command line. As always, we use the no-case modifier for user input fields. We enclose the command lines inside of parentheses and added an OR statement between them. If we want to add other command line processes, we could easily add them in this section. The other event we are interested in is the file creation event that occurs when the ntds.dit file is successfully created on the file system. For our example, we're monitoring a number of folder locations using Microsoft Sysmon. Because we don't know for sure where this file is going to be created, we have kept our criteria fairly broad using the regex expression and are basically looking for a file ending in .dit. The $ at the end of the regex means that it is the end of the field and not a substring. Because we don't expect to see a .dit file being created very often, or the ntds-util or VSS-admin with their respective command lines run very frequently, this might be a better option to use a sliding window with. We could improve this rule further by specifying just Active Directory servers as the systems this rule should run against, but we'll save that for another time. Let's go ahead and add the condition section. In our rule, we need a process and a file. There's no threshold needed, so our condition section is $process and $file. We need to join our events using a placeholder variable, and if we take a look at our UDM search, we can easily see in a tabular view that the principal.hostname is a common value in both the process and file creation events, so we can add that placeholder to both. For our match section, let's create this detection by grouping on that hostname value over a 2-minute window. Now, if we're using the default hop window, we would be done, but with the sliding window, we need to add our keyword of before or after and the event variable we are basing our detection around. Let's use our process event in the match section. Because we expect the process to trigger the file creation, we're going to add after $process to our match condition. Let's test our rule and see what we get. Here we can see we have 3 detections, and if we open our last one, we can see that we have 5 events. And by adding columns for target.file.full path, target process command line, target process file full path, metadata product name, and metadata product event code, we can see some additional supporting information, including the process creation in Sysmon and Windows event logs. Because we don't expect to see this process launched frequently, setting the process as the event that opens the window is a reasonable choice. Alternatively, we could modify this detection and capture any processes that meet our criteria that occur 2 minutes before our file creation event. If we change our rule and then go ahead and test with this criteria, we can see a set of detections as well. In our example, because the .dit file creation and the process launch of ntdsutil or vssadmin don't occur frequently, these are both good choices to use as the triggering point in our sliding window. However, if one of our events happened much more frequently, we would not want to start our window with that event. I realize that was a bunch of info on sliding windows, so here are a few things to keep in mind. The sliding window can look forward or backward in time around an event, and this time range can span 1 minute to 48 hours. Once that window is opened, all events that meet the criteria in the event section is going to be pulled in. The syntax for sliding windows is very straightforward. Just append the keyword before or after and the event variable to your existing match section. Finally, the hop window is the Chronicle default and can be used for many use cases, and by using the ordering functionality we talked about in earlier videos, you may find that it provides the granular control you need. However, if you find the need for a sliding window, Chronicle can support that as well using the concepts we just discussed and demonstrated. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to introduce a network function that quickly and easily can focus YARA-L rules on specific net blocks. The network function net.ipInRangeCIDR supports both IPv4 and IPv6 addresses. When using the function, we need to provide the UDM field that the IP address is in, as well as the subnetwork range in CIDR notation, enclosed in quotes. The output of this function is Boolean, that is, true or false. By using this network function within the event section of our rule, we can easily focus a rule on our specific net blocks. Whether your rule is observing traffic originating externally and moving internally, internal to internal, or internal to external, this network function can simplify your rule writing. We often see organizations crafting large regex strings to focus on their rules on specific net block ranges. This function is more performant than using a regex expression within a YARA-L rule, while being simpler to write and troubleshoot. Let's go ahead and take a look. To demonstrate how we can use the network CIDR function, we're going to build a rule that detects large byte counts from Corelight network connections. In our example, these network connection byte counts will be greater than 1 million bytes sent or received. These byte counts may be a little small for production environments, but hopefully it gives you an idea where we can take this. For those who have been following this video series, you might have noticed that we aren't aggregating our detections because we don't have a match section. Because we are focused on the network function today, we tried to keep our rules simple, but keep in mind that you can have match and outcome sections in this rule as well. Initially, our rule will not care about large connections between systems within our own network. We want to detect large connections when the principal IP address is not in our 10.128.0.0/24 net block, but our target IP is within that net block. Because IP address fields are designated in UDM as repeated, which means they can have multiple values, we are going to exclude any events that have a principal IP that matches our regex by prepending not to our statement. Our target IP criteria is simply that the field equals 10.128.0. This type of notation without the function is perfectly fine, and perhaps for a small network range is sufficient. Let's test our rule and see what we find. Here we can see that we have 3 detections from the same external IP to the same internal IP with sent bytes over 1 million in 2 cases and 65 million in the third case. Let's look at an equivalent statement, but this time we're going to use our network function net.ipInRange_CIDR. For the principal IP, we are going to continue by using the not operator and then use our function, and within the parentheses we have our field principal IP with the event variable of $network prepended to it, followed by a comma and the CIDR net block we want to compare our field to. Because we have some repeated values in that principal IP field, we've also brought the any statement within our function for evaluation. For the target IP, we've converted it to the same function, and then when we run this rule, we get the same results. Let's change things up here. This time, we're going to look at large byte connections between systems within our 10.128.0.0/24 address space only. We can easily do this by removing the not in front of our principal.ip function. When we test our rule, we get 9 detections. Now, suppose we had portions of our net block where large byte connections were totally fine, but others were a cause of concern. We could carve up our /24 net block and append an OR operator between our functions. In this case, we have a /28 within 10.128.0.0, which will convert our IP range to 10.128.0.0 to 15, and a /29 within 10.128.0.56, which converts to the IPs 10.128.0.56 to 63 that are of interest. Our principal range will continue to be the /24 net block, but with the target being these smaller blocks, we can test our rule and find 3 detections that meet our criteria. While we've just used a small network for our example, think about how this could be applied to a much wider swath of IP address space within a larger organization. Our example just covered IPv4, but don't forget the same concepts can apply to IPv6 and allow us to focus our rules on specific net blocks. The syntax is very straightforward, but we need both a field to evaluate as well as the CIDR range. Our output will be Boolean, so we don't have an equal sign on the other side of the function, and this function is most often used within the alert section of a YARA-L rule. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the Adoption Engineering team at Google Cloud, and today we're going to build a multi-event rule with a particular focus on ordering events for our detection. Our previous multi-event rule video talked about the basics of setting up the rule. This time we're going to discuss the time window a bit further, UDM time fields, and event operators that can all be used to order our events in a detection. By default, Chronicle uses a windowing technique called a hop. A hop essentially gathers all of the events that meet our rule criteria, no matter the time that it occurred. Now, that may be fine in some circumstances, but in some detections we want to know that event A occurred and then event B occurred and so on. Well, using UDM time fields and event operators, we can easily make this happen. Chronicle can also utilize sliding windows as well, but we'll save that for another time. Let's build a detection that informs us when a Windows user account is created, logged on, and then deleted. Since our last video had a rule with 2 different kinds of events, I figured we could dial it up and add a third event. Now, because we are still getting used to building multi-event rules, we're not going to be adding in a bunch of additional criteria for each event, but you can certainly add additional criteria to tighten your events further. Let's start by naming our rule Windows Short-Term Account Use and add our meta section to it. In the event section, let's start by adding the 3 kinds of events we are looking to detect: user creation, user login, and user deletion. Like our other example, we are looking for the existence of all 3 of these event variables in our rule, So let's go ahead and add them to our condition section now. From there, we need to determine a way to join these events and find a common value or values. For our example, we're going to go ahead and use a single join between a field in the creation event and the login event, and then the same join between the login event and the deletion event. To understand what fields I have available to me for my joins and event criteria, I'm going to use UDM search. Based on my search, it looks like the common field across all three events is the target.user.userid field. While we can use the UDM field name, I like using placeholder variables for my join, so I will use that. Each event type, defined by a unique event variable, will have a field mapped to that placeholder variable, and with that, the join's in place. As previously discussed, our match section is formatted as a match variable over a time window, ranging from 1 minute to 48 hours. Previously, we used a match variable that was the same as the field that we joined on. This time, I'd like to group my detection around a different field, the principal user ID field, and even more specifically, the user who created the account in the first place. To match on that field, we will create a placeholder variable for the field and then use it in the match section, and we want our entire sequence to occur within 1 hour from creation to deletion. If you build a similar rule for your environment, you could modify this window to whatever time range you see fit. Let's talk about the sequencing of our events for a minute. In our case, there's a logical flow. An account is created, it logs in, and it's deleted. Because our time windowing is a hop that collects all of the events that meet the criteria within the defined window, but doesn't take into account a specific order, we want to go ahead and enforce an order in our rule. While we could use a sliding window, I'm going to show you how easy it is to enforce the order in a rule with a hop window. We are going to do this by adding criteria using the event time along with the operators greater than and less than. Now, we know that the create metadata event time seconds will have a value less than the login event time. So we can start by adding create.metadata.event_time.seconds is less than login.metadata.event_time.seconds in our event section. Similarly, we can do the same between our login and our delete events. From a formatting perspective, you might be wondering if the criteria has to be in between the events, or can it be anywhere in the event section? It's a great question. They can be anywhere, but I like the events grouped together so that when I read the create to login sections and then the login to delete sections, those linkages form basically a bridge. All right, with all of that in place, our syntax is looking good and we can test our rule. When we do test our rule, we can see that we have a single detection and it appears that Tim Smith created a new user. If we expand our detection, we can see the underlying events, and if we add the columns principal hostname, source hostname, target user ID, since that's our join field, as well as the extension auth details and extension auth mechanism, we can see that Alice was created by Tim Smith, and it looks like the time from creation to deletion was about 50 minutes. We can see Alice logged into a Windows server, which was likely an RDP session since it is denoted as a remote interactive authentication, as well as authentications to the AD server from the Windows server. We could also see Tim deleted the user account. We could further expand this rule by adding process launch events to see what activities were performed after the login but before the deletion using the same method we just discussed. We just need to make sure that we have the correct UDM fields to join the others. When you're enforcing an order to your multi-event rules, remember that our default windowing is the hop, which is gathering the event within the defined window, but not actually ordering them. To order the events, we can use the UDM time field like metadata.event_timestamp.seconds along with the operators like greater than and less than. Remember that the hop window in the match section has a range from 1 minute to 48 hours. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to introduce statistical functions for standard deviation and variance that you can use as you build searches and rules in Google SecOps. Let's start with variance. You may know this by another name, which is mean square difference, and that name actually provides a few clues how we arrive at this value. Let's take the numbers on the right side of the screen and calculate the variance. First, we take the values in the dataset and calculate the mean, which is 6.6. Our next step is to calculate each value's difference from the mean and square that difference, which also helps us get rid of the negative numbers. We can add these square differences up to get the sum of the squares, which is 7.2, and to get the variance, we divide that value by the number of values in our data set, 5. Based on this, our variance is 1.44. The good news is that we don't have to do all of that math ourselves. The function window.variance does it all for us. We just need to provide the field or variable that contains that numeric value. This function assumes that the data in the rule or search is being aggregated, which means that there's a match section, and this function will be used in the outcomes section. Once we understand how the variance is arrived at, the standard deviation is a snap, because the standard deviation is the square root of the variance. In our example, if the variance is 1.44, our standard deviation is 1.2. Measures like variance and standard deviation can be helpful when looking for outliers because we often assume that data sets have a normal shape to them and that the bulk of the data is very similar in its characteristics, but there are outliers on either side of that normal distribution. These outliers would have greater variance and a higher standard deviation from the mean. Similar to variance, we don't need to do the math to get a standard deviation calculation. We just need to use the syntax window.stddev, standard deviation, followed by the numeric field or variable. This function also assumes that the data in the rule or search is being aggregated, which means that there's a match section, and this function will be used in the outcome section. Let's use these functions in a search and then in a rule. Our search will focus on Zeek HTTP network events that are coming to a specific server in my network, where the sent bytes are greater than 0. We can aggregate the results by the combination of the principal and target IP addresses. The outcome section will provide us with a method to count the total number of events, the average, the standard deviation, and the variance of the bytes sent. While our search is reasonably specific, that is focusing on a specific protocol and a specific product, my lab environment does not have very predictable traffic, so my variance and standard deviation look a bit wilder than a more tuned set of network connections. But hopefully this output gives you an idea of the kinds of things we can do with these statistical functions. Being able to search a time frame and gather standard deviation and variance and then refine it iteratively during a hunt can be useful as we hypothesize what might be driving our results. In our results, we can see our IP address pairs with an event count and the other measures. While it looks like some of our network connections are within a normal range, there are clearly some outliers. These functions can also be used in rules. The event section contains our criteria, while the match section contains our aggregation or grouping, with the addition of a 1-hour time window. The outcome section contains the event count, average, standard deviation, and variance. Finally, in our condition section, we have established a threshold for the number of events and the variance and standard deviation. Because the variance and standard deviation are mathematically linked together, remember the square root of the variance is the standard deviation. Having both is a bit redundant, but hopefully this drives the point home. When we test the rule, we can see a detection with a very high standard deviation and variance. The functions window standard deviation and window variance provide additional statistical measures that can be applied to data sets in searches and rules. The syntax doesn't get much simpler. We just need a numeric value from an aggregated data set to calculate the standard deviation and variance. Remember that standard deviation is derived from variance, so you can use one or the other or both, whatever you'd like. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the adoption engineering team at Google Cloud, and today we're going to build a multi-event rule with a focus on joining multiple fields and triggering our rule based on the condition of a threshold of an event that's been exceeded. Now, in previous multi-event rule videos, we have discussed joining a single field in each event. But what if we want our rule to have greater rigidity? For example, just because the event happened on the same system is not enough. It needs to be performed on the same system by the same user to merit detection. In addition to multiple joins in a rule, we also are going to look at the conditions that exceed a specific threshold. Previously, we were just looking for the presence of an event meeting our criteria, but perhaps we are seeing multiple events meeting the same criteria, and we only want to detect when a set of this criteria exceeds n number of times. We previously looked at the count in the condition when we were aggregating events in a single event rule. But this time we are going to build on this concept by mixing an event variable's existence and a threshold being exceeded by another set of event criteria. To illustrate these concepts, we're going to build a detection that triggers when a user account is attempting a login 10 or more times inside a 15-minute window, and then succeeds in logging in. For this example, we also want the system that we are attempting and succeeding to log into to be a constant as well. Let's start by naming our rule when repeated authentication failure then success. I've added the MITRE attack technique and subtechnique to my rule name as well and added a meta section to describe our rule further. In previous multi-event rule examples, we had very distinct event types. But this time, our events are very similar. The difference is that one has an event code and a resulting action denoting a failed login, while the other has a different event code and an action denoting a successful login. Let's use the event variables of fail and success to describe these sets of event criteria. Depending on our use case, we may want to choose to add more criteria, but this will work for our purposes today. We need to create our joins to link the failed and successful logins together. We can use UDM search to view our events in a tabular manner, and we can see that the principal hostname and the target user ID are the common fields that will be used to join our events together. Let's create placeholder variables for both fields in both the fail event criteria and the success event criteria. Now, let's get to ordering. We don't want 10 failed logins and a success in a 15-minute window. We want 10 failed logins before we see a success. We can force that ordering by adding additional criteria that says the fail criteria metadata.event timestamp seconds is less than the success metadata event timestamps.seconds value. With our event criteria in decent shape, let's move to the match section. We know our match window is 15 minutes, but what should we group on? We could group on the user or the host name. Could we group on both? Absolutely. Let's go ahead and do that and separate our match variables with a comma. All right, that leaves us with the condition section. In our previous examples of multi-event rules, we made sure that we had the event variables ANDed together in a condition, like this, $fail and $success. But wait a second. If we did that here, we would be looking for a single failed login and a single successful login in our window. To set a threshold on the number of failed logins, we are going to use the hash sign in front of our event variable rather than the $sign. The hash denotes in the condition that a distinct count of the variable is being performed. By the way, this hash could be prepended to a placeholder variable and generate a distinct count of a specific user ID, for example. But because we are prepending it to an event variable, we are generating a distinct count of the unique failed login events that we have. So our condition would be hash fail is greater than 9 and $success, because we don't need a threshold of success, we just need 1. All right, with all of that in place, we can see our syntax is looking good and we can test our rule. When we test our rule, we can see that we have a single detection and frank.coalesce appears to be attempting to log into the active dir system. We can expand the detection and see the underlying events associated with it. Notice how the event variables of fail and success are represented in each event. I didn't mention this before, but using a descriptive event variable pays dividends for analysts when looking at detections like this. Let's go ahead and add the following fields to our detection: extension auth mechanism, extension auth type, security result description, and source hostname. Notice that it appears that these are all network login attempts, and they appear to be due to a bad password. It's also worth noting that it looks like the failed logins appear to be occurring roughly a minute apart, so perhaps there is some sort of automated tool at work, and this detection requires additional investigation. With that detection example under our belt, remember you can join disparate events by 1 or more fields, which provides greater flexibility in how you craft your rules. Also remember that in the conditions section, all events in the events section need to be represented, whether it is with the $sign event variable denoting a value, or a hash event variable, or a hash placeholder variable that denote a distinct count that can be reached for the rule to trigger. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the Adoption Engineering team at Google Cloud, and today we're going to build our first multi-event rule and focus on joining disparate events together to accomplish this. Multi-event rules break a bit of new ground, but leverage all of the capabilities that single rules have and that we have already covered in earlier videos, including regular expressions, string matches, condition thresholds, and more. It's important to understand that unlike some single event rules, the match section is always required in a multi-event rule, so there will always be 4 sections: meta, event, match, and condition. To build a detection using multiple events, we will need to join our events together. These joins will occur in the events section and can use either placeholder variables or UDM fields. Finally, the condition section will need to contain references to every event contained in the event section. For our first multi-event rule, we will use event variables for each set of criteria in the event section. But as we build more complex multi-event rules, you will see other kinds of count conditions appearing here as well, but that will be a future video. Since this is our first multi-event rule, let's start off with a basic. Let's build a detection around the Windows event log being cleared. Depending on the datasets available, you might just want to look for the event type of system audit log wipe. But for our purposes today, we're interested in a specific process being executed from the command line that performs this action. Let's start by naming our rule Windows event log cleared and add in our meta section. In the events section, let's start by adding the 2 kinds of events we are looking for. First, we will create the process launch event and its criteria, and we will use an event variable of $process for this type of event. Second, we will create our system wipe event with this criteria and an event variable of $log. Notice how both of our events have additional criteria and we are using regex and string matching as well as the no case modifier. Because we are also looking for the existence of both of these event variables in our rule, let's go ahead and add them to our condition section now. With those components in place, we need to determine a way to join these events and find a common value. In this video, we will only use a single field to join our process and log wipe events, but in future videos, we'll incorporate multiple joins. I find that when building rules, it's useful to have a UDM search window open so I can view UDM fields in a tabular format that helps me find like fields that help me build my joins. In our example, we can see that the principal.hostname is a common field in both events, so we can use that field for our join statement. To join our events, we could use either the UDM field name or we could use a placeholder variable for the join. Here's what it looks like if we're going to use the field names. Notice all that we need to do is put in an equal sign between them. I generally like to put the joins between the two events as it serves as a logical spot when reading the criteria, but you could put it anywhere in the events section. With that said, I will often use placeholder variables instead for my joins. Sometimes those join fields are going to be used in the match section, and if you recall from earlier videos, fields don't belong in the match section, match variables do. One other question I get about placeholder variables is if the variable or the field should come first. The answer is that in the case of placeholder variables in the events section, it doesn't matter. I tend to go field and then variable, but for those with other coding backgrounds, variable to field works nicely as well. In our match section, we're going to set our match variable, and it's followed by the word over, followed by a time window. That time window can range from 1 minute to 48 hours. For this first example, we are not going to demand that one event has to happen before the other. We just want to know both of them occurred in the same window. Now, that isn't the case for all multi-event rules, so in future videos we'll discuss some methods to sequence one type of event before or after another. For now, let's set our window to 1 minute. All right, with all of that in place, we can see our syntax is looking good and we can test our rule. When we test our rule, we can see that we have a single detection that contains 6 events, 2 system wipe events, and 4 process events. When we add columns to our results, we can see which solutions generated logs for this rule, as well as the user performing these operations. Remember that when you start building multi-event rules, the match section, in addition to the meta, events, and condition sections, are all mandatory. UDM fields and placeholder variables can be used in the events section to join like fields together, and that each type of event that is being evaluated will have its own event variable. These event variables will end up in the condition section separated by the word and. As we evolve multi-event rules, other descriptors will be found in the condition section, but at the end of the day, each event needs to be represented in some way within the condition section. If you want to learn more about Chronicle, check out my blog called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to take a look at a time function that will format your time values in an easy-to-read format, but has the added benefit of customability. So, if the default form isn't what you're looking for, there are a number of different options to choose from. This function can be used as you build your searches and rules in Google SecOps. The timestamp values, while formatted in an easy-to-read format in the Google SecOps UI, may need to be manipulated when building rules and searches. The timestamp.getTimestamp function, without any additional arguments, will output the timestamp in the form year, month, day, followed by a space, and the hours, minutes, and seconds. This might be great for some organizations, but perhaps you require a different format for the date or just want to use a portion of the date. GetTimestamp does this for you by leveraging format elements. These additional formats align with Google SQL for BigQuery and are the second argument in the function, enclosed in quotes. The default is %f, %t, where %f handles the date portion and the %t is the time portion. The third argument in the function is the time zone and is optional. This will default to GMT. Because we can use these different format elements with the function, we could also easily isolate on the month, day, or even day of the week, all with this function. This link at the bottom of the page provides a listing of the different format elements that can be mixed and matched together. We're going to start by building a search that leverages network connection events that have a sent bytes value greater than 0. Here's our initial search. We're grouping our results by the date and the IP address, and sorting by the date as well as the event count. The date is based on the event timestamp, and because we have not added any additional arguments to the function beyond the field, we're returning the date in the format of year, month, day, hour, minute, seconds, and in GMT. That's fine for a start, but focusing our event counts by seconds may be a little too detailed for our analysis. Because our search is just focused on a single day, perhaps we want to just show the hour and the minute. We could do this by adding the second argument to our timestamp. If we take a look at our reference of date format elements, we can see that %R will return hour, minute in 24-hour time. Because our search time window is less than a day, perhaps we don't need the date. So let's add the %R to our function, which returns the time in hours and minutes. Now when we run our search, we can see our data is now aggregated by this new value. Maybe we do need the date in our output, but we don't want it to be in the default format of year, month, day, and would prefer to have it in a format like month, day, year, followed by the time. The function reference indicates that this date format is denoted by %x in lowercase. So let's add that to our function and run it again. Now, just a quick side note, you might be looking at the results and seeing lots of low event counts and thinking, can we roll these up to the hour? The answer is yes. We can do this by changing the %R to %H, which returns the hour in the form of 00 to 23. And then I've added :00 to our date. When we run that, notice the time rolls up to the hour. All right, let's get back to our date with the hours and minutes in it. We could keep working through additional examples to change and modify our grouping value, but rather than doing this, I'm going to demonstrate a few more time format examples in the outcome section of our search. The first one is taking elements of the timestamp and arranging them in a format that aligns to my needs. In this case, a 2-digit year followed by the month spelled out and then the day. Notice I'm outputting the time based on a 12-hour clock with AM/PM options as well. And in the first example, because I have not specified a third argument, we have defaulted to GMT. The second example is very similar, but with two modifications. The first is that the %A provides a day of the week to the timestamp, and the second is the time zone argument asks for the date and time in the time zone that Los Angeles is in. When we run our search, we have two more columns all representing the same time, but in different formats and a different time zone in the case of the last column. There are a number of ways to utilize the timestamp.getTimestamp function, including isolating portions of the time into a placeholder variable that can be used elsewhere. These concepts can also be applied to rules. The timestamp.getTimestamp function provides us the ability to take a timestamp value, extract portions of the date or time, as well as change the formatting for display purposes to more easily work with our data sets when hunting, building detections, or developing reporting. This function accepts up to 3 arguments: the field or variable with the timestamp, the format we want the timestamp to appear in, and the time zone. The time zone is always optional and will default to GMT. The format element defaults to %F%T if not provided, which will return the year, month, day, hour, minute, second. So, if you would prefer something else, make sure you use the format elements and enclose them in quotes. Finally, remember that portions of the timestamp can be extracted to variables that can then be used in our searches or rules, either to aggregate data, output as an outcome variable, or perhaps use as a condition in a rule. This function provides a great deal of flexibility when working with timestamps and can be applied to your hunts and investigations. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to take a look at a time function that takes a string that is formatted like a time and convert it to a timestamp, which can then be used with additional time functions. Mind-blowing, I realize, but don't worry. we'll walk through a couple different ways that we can use the timestamp as Unix seconds function today. And like the other functions we've been discussing, it can be used as you build searches and rules in Google SecOps. On occasion, we might find ourselves with a date time value in a string field. It doesn't matter how it got there, but it's there and we want to use it just like we would any other timestamp. This can be challenging because it's a string, and at this point, how can we calculate a time difference between two strings? Luckily, the timestamp as Unix seconds can help us. This function does expect the string format of the date to be in the form year, month, day, hour, minute, second, or for those who watched our previous video on timestamp.getTimestamp, the format element of %f%t. However, once our string is in that format, we can use the other function with the single argument of the field or variable and output an epoch time value that can then be used with other functions. Due to the value moving from a string to a timestamp, there may be a number of other nested functions used to accommodate this, including strings.concat or strings.substring, not to mention other timestamp functions if performing a comparison. But we have videos on these if you need a refresher on any of this. Let's put this into practice. We're going to start by building a simple search for GCP firewall events. In our output, we have a series of parsed and extracted fields from the raw data. My instance doesn't happen to have a bunch of dates in string fields, so these extracted fields serve as an excellent surrogate because the extracted field is a string but contains a time value. In case you don't believe me, let's do a quick test. A common time question is, what is the difference in time between when my event occurred and when the event was received? To find the answer, I could add an outcome section to my search and calculate the date difference by subtracting the value from the extracted received time field from the event time. When I add my statement, I get a compilation error because the search is expecting an integer or float value instead of the extracted field, which is a string. Let's try something different. I'm going to go ahead and paste an example of the extracted field into my search and comment it out. You'll see why in a minute. And I'm going to go ahead and add a few lines to my outcome section. We're going to use our timestamp as Unix second function to convert our date that is a string, and we're going to go ahead and display the event time, and then we're going to go ahead and calculate the difference between these two values. Notice now that my search compiles. I'm feeling pretty good until I see the results. It appears the converted Unix timestamp is -1 for all the rows. The reason for that is the conversion from string to epoch is specific in the format. Notice in the example value that I pasted in as a comment above. Now, having done some testing, it isn't so explicit that it can't handle the T that separates the date and the time, as well as the decimals below the second level. But clearly in this case, we can't just use our function and call it a day. Let's take a look at a few different ways we could prepare our string to work with our function. This is where string functions like strings.concat and strings.substring come into play. The format has to be year, month, day, hour, minutes, seconds. I'm going to show you 3 ways that this worked for me. The first method is working across the entire string and including the T using the substring function and collecting the first 19 characters of the string. The second example is grabbing the first 10 characters for the date, concatenating a space, and then taking the 12 characters starting in position 12 of the string to collect the time, including the 3 decimals under a second. The final example is being a bit more strict and just collecting the date and time and leaving out the T and the subseconds. When we test our search, we can see that all 3 of these are valid approaches, and the result is a nice epoch value that can be used with the event time to generate a time difference in seconds for the firewall logs. Once a string is converted to a timestamp, we can do more with it, both in a rule or a search, but hopefully this highlights how we can convert a date in a string field to an epoch value. The timestamp as Unix seconds function converts a date value in a string to a timestamp that can be used in time operations and is very simple to use. You just supply the field or variable the value resides in. That having been said, it does require a format of year, month, date, hour, minute, second. And because of that, variables like strings.concat and strings.substring may need to be used to format the string properly before converting it. The good news is that once the conversion occurs, these values are treated like any other date and timestamp function for formatting or other logic that can be applied to them as needed. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the adoption engineering team at Google Cloud, and today we're going to talk about YARA-L variables. Now, there are 4 kinds of variables that we use in rules: event, placeholder, match, and outcome. Today, we're going to cover the first 3 and save outcome variables for another time. All variables are referenced with a $sign followed by the variable name. Now, let's go ahead and look at these variables in action within a rule. Our example is looking for repeated failed logins followed by a success. Now, there's a lot going on here, so don't worry if it all doesn't come together just yet, because we'll come back to this rule again. For now, let's focus on how our variables are used. Let's start with the event variable. You can find the event variable in the event section. The event variable is prepended to the full UDM field it's associated with. Every line of criteria in the event section will have a variable in front of the UDM event or entity fields. If we're looking for a single event or a single set of events with the same criteria, we might only have one event variable. However, in this case, we have 2 event variables, fail and success, because the criteria associated with the failed events is different than what is associated with the successful events. While the name of the event variable can be arbitrary, using a descriptive name can be beneficial for analysts reviewing the events because these variables are represented in detections. I went ahead and ran the test rule function on our rule, and here we can see that the variable names of fail for these underlying events are followed then by our success. Having these in place like this make it very easy for an analyst to look and understand which events are which. Another kind of variable is the placeholder variable. Placeholder variables, shown here, are pretty flexible. Once you define one in the event section, they can also be used in the match, outcome, or condition sections. In our example, we have 2 placeholder variables, $hostname, as well as $user. Notice how we have placeholder variables defined in both the success and the failed events. Those placeholders can then be used in the match section where they become our match variables. I feel I should mention that because you are using a placeholder variable, that does not mean it has to be in the match variable section as well. In this case, it just happens that they are. Match variables are needed to have a common value or values across disparate events that we want to join together. Match variables are always followed by a time boundary. In this case, our match section states we are grouping events with common user and hostname values that occur within a 15-minute time window. For those familiar with SQL statements, this would be analogous to a group by section. So those are our 3 variables in action, but hang on a second. If we go down here to the bottom to our condition section, we can see our event variable of success with a $sign in front of it, but the event variable of fail has a hash symbol in front of it. What does that mean? Well, the hash is a special character that can be used in place of the $sign in the condition section. When setting our conditions, we always need to use event or placeholder variables. $success as we can see here, means that a success event must exist. If we just wanted one failed event followed by one success event, we could say $fail and $success, but that could be a pretty noisy rule. Instead, we can use #fail, which generates a distinct count of events that satisfy our event criteria within our time window. It's worth mentioning that you could do the same with a placeholder variable to get a distinct count of values in a specific field, but more on that another time. Because we have set our condition to #fail is greater than 4 and success, we need to see more than 4 failed events followed by at least one success event within the 15 minutes that was defined in the match section associated with the event criteria that we defined. And that's how variables can be used in YARA-L. That might have seemed like a lot, but we will have a lot more examples coming. Just remember that event variables are used to organize like criteria together. Placeholder variables can be used throughout the rule to describe different fields, and match variables link disparate events together within the match section. If you want to learn more about Chronicle, check out my blog called New to Chronicle for more handy tips, and engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the adoption engineering team at Google Cloud, and today we're going to build a rule that aggregates multiple events into a single detection. To aggregate events into a single detection, we're going to introduce a new section to our YARA-L rule. This section is called match, which is used in addition to the meta, events, and condition sections we have previously covered. The match section provides a method to group data over a time boundary that can range from 1 minute to 48 hours. With the introduction of the match section for aggregating events into a single detection, we are also going to start using match variables, which we have previously discussed. These match variables are basically taking placeholder variables from the event section and using one or more to match like events in our detection. Now, as we build rules in Chronicle, you'll likely have the match section in many of your rules. You might be wondering why. Well, if I'm logging Windows events and using an EDR or sysmon on the same host, and I detect a process execution, I would likely get a detection for each of these data sources. While it's great that we can detect this, presenting our analyst with what is basically a duplicate detection, one for each event source, is not ideal. But by adding the match section to our rule, we can aggregate these events into a single detection. Let's take a look. We're going to use our Who Am I rule that was introduced in our single event rule with string matching example and demonstrate how we can aggregate our detection. We already have our rule in place from our earlier example, so we just need to make a few tweaks. One of the biggest considerations we need to take into account is what field or fields do we use for our match condition. To see what our current detection looks like, we've already run our test rule to examine our results. By clicking on the Columns button, we can add additional fields into our detection to view values. Here we can see that principal.hostname and principal.user.userid both have the same value occurring roughly at the same time, and there are different product event codes and event sources, 4688 for Windows events and 1 for sysmon events. With that background, we need to ask ourselves, how do we want to aggregate our detections? Maybe we want to group by the command line that was executed. We could add our match section below the event section in our rule and add our field. But wait a moment. We can't add a UDM field here. We need a match variable. In the event section, let's add a placeholder variable for the field target.process.command_line, and then take that placeholder variable and apply it in the match section of our rule. As previously mentioned, the match condition time range is 1 minute to 48 hours. For our example, we're going to use 1 hour. When we test our rule, we can see we get a single detection with 4 events in it. This is because all 4 events with the same common match variable occurred within the same time range. Let's change our match to the principal.hostname field by setting our placeholder and match variables. We will keep our time window the same and then test our rule. Notice this time that we have 2 detections, one for each hostname. Remember, matches don't need to be based on a single variable. This time, let's match on both the hostname and the user ID. To do this, we can add a placeholder variable for the user ID in the events section and then use that variable in the match section. We will separate the match variables with a comma. When we test our rule this time, we get 2 detections again, grouped by both the host and the user ID. As always, once we're happy with our rule, we can click Save in the top right corner of the rule editor and close out. Now, when aggregating events and rules, remember that we want to go ahead and add the match section to our rule. Without this, we will trigger a detection every time our criteria is met, which might get unwieldy for our analysts. When we do build that match condition, we are grouping common events by time. This time range can be between 1 minute and 48 hours using the syntax of variable over time. Finally, UDM fields do not appear in the match section. Instead, we use placeholder variables that we define in the events section and can use one or many separated by commas in the match section. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the adoption engineering team here at Google Cloud, and today we're going to talk about YARA-L operators and modifiers. When it comes to YARA-L rule building, we need a way to build event criteria for our detections. Operators and modifiers provide some of the essential tools in our toolkit to make this happen. When working with repeated fields, we also have any and all, which help us work with those fields as well. Let's start by taking a look at modifiers and operators in action. Our first example is going to be working with an unusual location link file rule. And or not can be used within the event section to build out search criteria, and is assumed in the absence of other operators. Here we can see that our rule has 4 different event type values, and we are using parentheses and the OR operator to logically group this portion of our criteria. The second part of our criteria is looking for strings within the target file full path field. Now, we aren't going to get into regular expressions just yet, so don't worry about that, but let's look at our modifiers and operators. The operators between the end of the parentheses and the other fields are all optional because they are outside of the parentheses. If they were inside the parentheses, you would need to have the AND operator or you would get a syntax error. Notice in the top corner of our rule, the green check switches to a red X sign if the syntax isn't correct. It's a handy tool for reference. Also notice the not prepended to the second file full path criteria. Basically, we're looking for link files in folders other than desktop, documents, and start menu. If we wanted to look in those specific places, we could just remove the not. No case is used by appending it to the end of a field and value and gives us a lot of flexibility when matching against command lines and other fields that contain user input. With no case, I don't need to worry if a folder, command, user, whatever, is mixed case, uppercase, or lowercase. It just takes the guesswork out of it. However, it's important to note that for enumerated fields, like event type, no case will throw a syntax error. That's because all enumerated fields are always uppercase only. If you're wondering which fields are enumerated, the UDM field list covers this. It's a great reference to have handy. Our other rule is really simplistic, but it highlights how the any and all modifiers can work with repeated fields. Repeated fields handle items like multiple IP addresses associated with a system. Here we are looking for a user login from a system that has a specific set of IP addresses. Because IPs are repeated fields, specifying principal.ip equals x and principal.ip equals y would fail because how could a field be two values at the same time? However, by prepending the word any to both pieces of IP address criteria, it allows us to look through all of the repeated values for that IP address and say basically if any of the IP addresses that match this first string and any of the IP addresses match the second string, we meet our criteria. The term all works nicely if you're saying all IP addresses do not equal a value. Generally, a good rule of thumb is to use the any and all terms whenever you're working with a repeated field. You will see more rules that build on these concepts, but for now, remember that and, or, and not are used to link different event criteria together with the help of parentheses. No case takes the guesswork out of fields that could have different values in mixed, upper, or lowercase. Any and all help with repeated fields to give more flexibility to find the values we care about most. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips and engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the Adoption Engineering team at Google Cloud, and today we're going to talk about YARA-L and how rules are structured. Detections engineers need a method to build rules that will alert when suspicious or malicious behavior is taking place. Chronicle uses YARA-L to build these rules. YARA-L is a variant of the virus total YARA rule, but is focused on log data. It can be used to detect threats in both historical and real-time events, and it's leveraging the Unified Data Model, or UDM, the schema that Chronicle stores event data in. Now, if you're new to Chronicle, don't worry. We aren't expecting to build a rule with all of these components today, but we are here to help show you what you can do and what you will be able to do. All rules contain three required sections: meta, events, and rule and condition. While the other sections are optional, they provide you more benefits. Let's look at an example rule to get a feel for all of these sections. Now, the rule might look daunting at first, but let's walk through sections one by one, and you'll see that it's got a pretty logical flow. The meta section at the top describes the rule. While users often keep this section brief, adding values like author, severity, description, and priority can be surfaced when reviewing the rule and used in alerts, which can provide valuable context. Notice in our example, we know that this rule is for Windows events, addresses a MITRE attack technique of OS credential dumping, and uses data sets like Microsoft Sysmon and Microsoft Windows events. The events section contains fields and values of interest that we want to observe. Functions, joins, and other comparisons can occur here as well. This is similar to a where clause in a SQL statement. For this rule, we are looking for the value process launch in our metadata.eventType field and the string mimikatz in the target process command line field. Don't worry about the $ variables for now. We'll get back to those in the future. The last mandatory section is down here at the bottom, which will include event variables that are needed to be met for the rule to trigger. In this example, there's only one condition, so there's only one variable, which is part of the $ process variable we used in events. We have two optional sections in this rule. Match aggregates values over a time window and will be used extensively with rules that rely on more than one event to trigger. They are aggregated over a time window that the rule writer defines. Finally, we have the outcome section. This section provides the ability to add additional context and scoring to a triggered rule. These values can be leveraged within Chronicle for dashboarding and alerting, as well as into a SOAR or ticketing system. If you're just starting with YARA-L, we will build on this structure in subsequent videos. Just remember, we always need meta, event, and condition sections in our rule. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips and engage the security community at googlecloudcommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we are going to introduce the statistical function for median that you can use as you build searches and rules in Google SecOps. The median is calculated by taking all the values in a dataset, ordering them from least to greatest, and then finding the value in the middle of the results set. Using our example here, we have a sample set of 5, so the middle would be the third value in the dataset. In this case, the third value is 2, so while the average is 2.8, the median value here is 2. If there is an even number of values in the sample set, Google SecOps will choose one of these values non-deterministically. The median function is window.median and requires 2 arguments, the numeric field or variable that is used to calculate the median, as well as a Boolean argument to ignore 0 values. The window.average function does not require this Boolean condition, but the window.median does. This function assumes that the data in the rule or search is being aggregated, which means that there is a match section, and this function can be used in the outcome section. Let's start with a search of network connections and then aggregate the results by the combination of the principal and target IP addresses. This generates a listing of IP addresses in our search window. We can add the outcome section to perform a number of calculations based on the aggregated or grouped IP addresses. For our example, we have a count of all of the events in our results set, as well as counts of the number of events that have a network sent bytes value of 0, and a separate count of non-zero values. Notice we're using sum as an aggregation function for these 2 outcome variables. In a previous video, we covered average, and it's included here to help illustrate the difference between the average and median. We characterize the average in 2 ways, one that takes into account 0 values and one that does not. We're going to do the same here with median. The reason why is that my network connection set contains GCP events, Sysmon, Corelight, and other data, some of which contains byte counts and some that do not. For demonstration purposes, I want to show what an excessive number of 0 values can do to my calculation and why it's nice to have the option in the arguments to include or exclude 0 values. Again, there is applicability for both approaches. I just want to show you that there are options. In our results, we can see our IP address pairs with an event count and the subtotals. Notice some of our results do not have any non-zero values, and consequently, the median is 0. For pairs that have a mix of 0 and non-zero values, we can see a disparity in our median as well as our average. I find it can be interesting to see how large the range can be between a median and an average, which also highlights outliers in the results set. Functions like median can also be used in rules. We can adapt our search to build a rule easily. The event section contains our criteria, the match section contains our aggregation or grouping, and we have added a time window of 1 hour. The outcome section contains the event count, average, and median, and we have the Boolean argument of true set in both to ignore the 0 values. Finally, in our condition section, we have established a threshold for the number of events and the median value calculated within the 1 hour window between the 2 IP addresses, which will be our trigger to detect. When we test our rule, we can see that we have an IP device pair that has exceeded the event count and the median sent bytes threshold. We can display these values along with the average. The window median function provides another method to generate a statistical measure. The syntax is very straightforward, but it does require 2 arguments: the field or variable that is being calculated, as well as a true or false to denote whether 0 value bytes should be factored into the median calculation. True will ignore 0 values, false will include 0 values. Finally, functions starting with the word window are viewed as aggregation functions, much like max, sum, and count. So additional aggregation functions prepended to it in the outcome section are not needed. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to introduce statistical functions for mean and mode that you can use as you build search and rules in Google SecOps. Mean, also referred to as average, is calculated by taking a set of numeric values, adding them up, and dividing by the number of samples to arrive at a result. While this measure often provides a value around the middle of the sample set, outliers on either side can skew this number. We will cover median in another video as a potential remedy to this. In the meantime, the function for average, called window.avg for average, accepts two arguments, the numeric field or variable that is going to be used to calculate the average, as well as an optional Boolean argument to ignore zero values. If it is not included, it defaults to false and includes all values, including zero values. This function assumes that the data in the rule or search is being aggregated, which means that there is a match section, and this function will be used in the outcome section. Mode is very straightforward. It returns the value that is most frequently seen in the dataset. The function for mode, called window.mode, accepts a single argument, the field or variable it's observing. This function assumes that the data in the rule or search is being aggregated, which again means that there is a match section, and this function will be used in the outcome section. But it can work with numeric fields as well as string fields. Let's look at both of these functions. We'll start with a search of network connections and then aggregate the results by the combination of the principal and target IP addresses. This would generate a listing of IP addresses in our search window. We can add the outcome section to perform a number of calculations based on the aggregated or grouped IP addresses. For our example, we have a count of all of the events in our results set, as well as counts of the number of events that have network sent byte values of 0 and a separate count of non-zero values. Notice we are using sum as an aggregation function for these two outcome variables. Now, let's turn to our new functions. We can characterize the average in two ways, one that takes into account zero values and one that does not. My network connection data set contains GCP events, Sysmon, Corelight, and other data, some of which contain byte counts and some that do not. For demonstration purposes, I want to show what those excessive number of zero values can do to my calculation and why it's nice to have the option in the arguments to include or exclude zero values. This is not a right or wrong way to do this. This is just about providing options. Finally, we add the windows.mode function to our search. In our results, we can see our IP address pair with an event count and the subtotals. Notice some of our results do not have any non-zero values, and consequently, averages are all 0. For pairs that have a mix of 0 and non-zero values, we can see a disparity in our average. Notice that mode in all of these cases is 0. This is because the most frequently seen value is 0 in our results set. Let's change our search and add a line of criteria that says sent byte has to be greater than 0 and rerun our search. Now we get mode values that are non-zero. Mode can also be used with string values. Here we have a search that is looking for process launch events where the process file full path cannot be null. We can group or aggregate with the principal hostname and then generate a count of events as well as a mode of the most frequently seen file path values during our search window per device. We could also use these functions in rules. If we wanted to take the first search we built and convert it to a rule, we could easily do that. The events section contains our criteria, the match section contains our aggregation or grouping. We just need to add a time window so we are aggregating events over a 1-hour window. From there, we're calculating the event count and average, again ignoring the 0 value, and then in our condition section, we have established a threshold for the average bytes between the two IP addresses, which will be our trigger to detect. When we test our rule, we can see that we have an IP device pair that have exceeded the defined threshold for 1 hour. This is a basic rule, but can be broadened and customized for more specific use cases. As you can see, window average and window mode provide a method to generate statistical measures by aggregating a dataset to find the average or most frequently seen values. The syntax is very straightforward for both, but average does provide an extra Boolean argument that allows us to take into account zero-value fields. Functions starting with the word window are viewed as aggregation functions, like max, sum, and count. So, additional aggregation functions prepended to it in the outcomes section are not needed. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to introduce a string function that takes base 64 data and decodes it in search and YARA-L rules. Now, we don't often see base 64 data sitting all by itself within a UDM field, so this command is often applied to placeholder variables or nested with other regex functions. In our last video, we discussed the re.recapture function and how we are going to build on this concept and then use the base 64 decode function to uncover what lies beneath the encoding. Base 64 can often be used to obfuscate code, so having a function built into Google SecOps to work with this data can streamline detection and response. The function is very straightforward, just pass the encoded string to the function, so really the question becomes, do we read it in directly from a regex function to capture the base 64 string, or read a placeholder variable where the base 64 is already being held? Let's take a look at it in action. Our rule builds on the example that we had when we looked at re.recapture. That is, we're looking for encoded PowerShell strings within the target process command line. Here are our detections when using the re.recapture function. Now, at this point, we could copy and paste our string into a decoder, but that's an extra step and requires us to pivot away. It also doesn't allow us to work at scale with multiple encoded PowerShell events. But with the strings base 64 decode function, we can add this logic into our search or rule, and it just happens. In our first example, we have the encoded string already captured and written to the placeholder variable encoded value. To create a placeholder variable with the decoded value, we could copy our logic from the encoded value that includes the capture function and then encapsulate that with our strings base 64 decode function. Now we have a placeholder variable for both that can be used in the events section of a rule, or we can use those placeholder variables and statements in the outcomes section to format these fields in our detections. However, if we just need to output this decoded value in our detection, we don't even need to put this nested set of functions in our events section. We could just create our outcome variable and use our nested functions to output it there and be done. Either way, when we test our rule, we can see that we have the decoded PowerShell, and we can see the multiple detections where we now have actionable information to dig into and assess if the encoded PowerShell events are suspicious or not. With all of these functions, there is some variability how they can be deployed, so these are just a few ways to use these functions. As you can see, strings.base64_decode is very straightforward to use and provides analysts with a method to gain visibility into base 64 encoded data without having to copy and paste out to CyberChef or some other system. However, because base 64 is often not the only value within a field, a combination of regex functions and placeholder variables are often used to work with this data. As you saw from our demo, the formatting of the base 64 may make it a bit tricky to work with if we are performing additional analysis on it. With that in mind, next time we're going to look at one additional regex function, re.replace, and we'll show you how you can tidy up your decoded base 64 to work with lists and other logic. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to introduce a string function that quickly and easily allows us to convert a values case to all upper or all lower capitalization. This can be applied to rules in YARA-L and is incredibly useful when dealing with fields that contain variability when compared to other data sources or lists. The string function to upper and to lower provides us another method to work with values where case is variable. We've previously discussed the no case modifier, but here we will put our functions and the modifier into practice. The syntax for our functions is strings.toUpper or to lower, followed by the field name prepended with the event variable. These functions can be used to compare a field to a value, or it can be nested as part of some additional criteria. Let's take a look at it in action. Our example rule is leveraging the same general rule we used for regex reference lists. Essentially, we are detecting process launch events from Microsoft Sysmon for hosts in our domain. Because we are going to look at data in the target process file full path field, we are going to require that this field is not null so we don't end up with extraneous detections. And we are grouping our detections by the host name over a 5-minute window. In the outcome section, we're generating a count of the number of events within each detection, as well as an array of the distinct values for the target process file full path, since this is the field we will be using with our regex reference list. We also have a line of criteria that compares the target process file full path to our regex list lolbin_regex. If we tested this rule as it is currently written, we end up with 0 detections. What happened? I set you up on this. Notice in the principal host name we have a domain that is all capitalized. It turns out that in our events, this field is not all caps, and without a method to handle the case, we get no results. With a field and value, we can handle this in a few different ways. The first way, and we've discussed this in earlier videos, is to use the no case modifier, which really is the most forgiving way to handle this. The other method is to use the functions strings.toUpper or to lower, it's up to you, and compare that field to some value, in this case, the regular expression of our domain. Either way, we get 7 detections. Now, let's take a look at our regex reference list called lolbin_regex. If you watched our regex reference list video, we discussed the challenges with case sensitivity and how we could use the (?) close parentheses as part of RE2 syntax to handle case sensitivity within the list. However, I can understand not wanting to have to go into lists and prepending that to every row. Instead, we can use our function strings.toLower or to upper, depending on your list. Here we are calling the strings to lower to take the values in the target process file full path and convert them to lowercase before comparing them to the regex reference list lolbin_regex. When we do this, we get 11 detection, including those pesky SQL command.exe target process file full path values that were omitted before, without having to handle case sensitivity on a row-by-row basis within the list. Could we use no case instead of the to upper or to lower function? Sure, we can append no case to the end of our criteria. As you can see, there are a few different ways to work with values that have mixed, upper, or lowercase characters in them. If you know what the options are, you have many tools at your disposal. As you can see, strings to upper or to lower provide additional flexibility when working with fields and values that may have upper, lower, or mixed case in them. This can also extend into different events where a join is needed to link those fields together. The syntax for these functions requires the function and the field that is being converted and can be used as a comparison against a value like this, or the function can be nested with other functions. No case is another option we have as well, so know that the function and no case are both available and choose the one that's best for your needs. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to take a look at a function that will help us extract a substring from a string based on an initial position and length. This function can be used as you build searches and rules in Google SecOps. Sometimes we have string values that we want to extract a substring from, but we don't want to use a regular expression. One method we can use to extract the substring is to use the strings.substring function and specify an integer value where the substring starts, followed by a length. The length argument is optional, and if it is not specified, the substring will continue until the end of the value in the field or variable. If we want to capture the first character, the first argument can be the integer 1. If you want to specify 0 or even a negative number, that won't hurt anything, it'll still start at 1. A few common ways to use this function include outputting the substring to a placeholder variable that can then be used for aggregation or displaying it in the outcome section. Another option would be to output the substring and then compare it to another string. Let's take a look. We're going to start by building a search that leverages HTTP events. These events are from the Microsoft Graph API activity logs. In this example, we're going to determine which applications have been enumerated by a service principal. An adversary who has access to the Graph API may want to determine if they can access APIs through different applications, and this enumeration is a way to discover applications and their permissions. Our initial search looks like this. We're using the re.regex function to identify the specific API call of interest, as well as the method and response codes. When we take a look at the URL field in our results, we can see that there is a common layout and GUIDs reside in the directory structure. There are a few different ways that we could approach this. There isn't a single right or wrong approach, but it's worth mentioning a few that jump to mind. Let's start by doing nothing and just grouping the URL. This gets us a count of unique URLs, but since we know the pattern of the API endpoint, do we really want the entire URL in our result set? If we want something other than the entire URL for presentation, we're going to need to use a function to extract that substring. We can use our string.substring function and start counting from the beginning of the string. There are 59 characters before we get to the GUID we want to extract. Keep in mind that with the substring function, we are counting from 1 for each character. If we want to just start collecting data from the start of the value in the field, we could specify 1 or 0. It'll default to the first character. The second argument is optional, so we don't have to define a length, but if we don't, then we'll get the rest of the values after the GUID, and we end up with this. While the complete URL is no longer displayed, we still have the trailing /members after the GUID. We can fix this by specifying a length of 36 for the GUID. Now we have a GUID with its associated count. That's the basics of strings.substring. Now, if you're like me, you might not want to have to count 59 characters into a URL to get to the point where we want to start extracting the substring. We could also use other functions to make this simpler. Let's use the regex replace function, re.replace, to strip off the leading portion of the URL, those first 59 characters, and replace them with a null value. From there, we can then start counting at the first character. I specified 0, so it's the beginning of the string, but 1 is fine as well, with a length of 36. Again, we get our GUID with our event count. It's worth mentioning that if we wanted to use re.capture with a regular expression, we could do that as well. One more thing to mention on this. If we wanted to search for a specific GUID in our filtering statement, we could do this too. Here is one method. Notice that rather than using a regular expression, we could use the strings.startsWith function to find HTTPS URL strings and then search in the string for a specific GUID. As you can see, there are a number of ways to accomplish this. These same concepts all apply to rules. The function strings.substring provides us the ability to extract a substring from a field or variable based on a start position and length. To use this function, we require the field or variable followed by the start position with that optional length. A start position of 1 or 0 will be the start of the string, and if no length is specified, the length will default to the end of the string. The output of this function can be used in a few different ways, whether to filter on a specific value or to extract a substring that can be used for aggregation, or used in the outcome section of a rule or search. Finally, it's important to remember that there are a number of different ways to do what we've just done, including using a regular expression. The point is that there isn't a single right way to solve a problem. This is just another tool in the toolbox that can assist you as you hunt, investigate, or detect suspicious activities. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site, and we're continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to introduce the string function of length that can be used as you build searches and rules in Google SecOps. String length can be calculated with the use of the function strings.length. This function will count the number of characters in a string field and output an integer value. As you can see, the syntax is very straightforward. Just provide a field or variable that needs to be measured. This function can be used in a search or rule to narrow the data set by setting it in the filtering statement of a search or in the events section of a rule, or it can be used in the outcome section to calculate a statistical function based on the integer output. Common use cases that the length function is applied to include measuring command lines, user agent strings, and DNS queries for anomalous values based on their string length. Let's take a look at a few examples. We'll start by taking a look at network HTTP events and hypothesize that user agent strings that are excessively short or excessively long are of interest to us. To narrow our results a bit, we've removed any events that don't have a user agent string, as well as the pesky IPv6 address of : 1. To get started, I want to review some broader statistical measures, so we are grouping all data for the past week together, calculating the length of the user agent strings, and then using statistical functions of count, max, min, average, medium, and standard deviation to generate values. In our results, we can see that we have over 200,000 events with a max length of 269 and a min length of 3. Additionally, we can see that the average length is 20 and the median is 14. Let's refine our search and just look for the events that have a user agent length of 5 or less, since we know the minimum is 3. While we're at it, let's group the results by IP address pairs. When we run our search, we can see a few IP addresses, each with the same 2 user agents. The first is TNAS, which is associated with a vulnerability scan for the TerraMaster NAS, and the other is RPC, which upon further analysis appears to also be part of the same vulnerability scan. Because we can also use strings.length in rules, let's take a look at what that might look like. Let's build a rule that looks for excessively long command lines. The thought here is that perhaps abnormally long command lines may be anomalous in the environment. With any rule, some tuning will be required, so while we are focusing on process launch events, we filtered out a few specific executables and folders to get a decent signal-to-noise ratio. We're grouping process launches by the host in a 30-minute window, and in the outcome section, we're calculating an event count and generating statistical values of max, average, and standard deviation based on the length of the command line. With those values, we can then also calculate the outlier value that is 5 standard deviations away from the average. And because we want to return just the longest command line in the window, we're going to use the window.last function to get us this value. More on this function will be forthcoming. Finally, we're going to compare the longest command length to the 5x outlier value. And if the command line length in the time window is greater, we're going to generate a detection. When we test our rule, we get a few detections, and when we review them, we can see that perhaps some additional tuning may be required, but we can also see that at least one of these detections contains a number of reconnaissance commands under a single process launch. This isn't something that we might expect to see from an internal user, so there may be some additional investigation required of this system. The strings.length function provides us the ability to generate an integer value based on the number of characters in a string and then apply additional criteria to this value. The syntax is very straightforward. Just provide the function along with the field or variable that we need to calculate, and then depending where the function is used, it may require an aggregation function like max or min to be prepended to it along with the outcome variable, or it could be used as a threshold value in the condition section of a rule. This function can be used in the filtering statement of a search, in the events section of a rule, as well as in the outcome section. It just depends if this value is designed to filter out data or is part of a computation. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to introduce a string function that counts the number of substrings within a field. This function can be used as you build searches and rules in Google SecOps. Strings.count substrings quite simply counts the number of substrings within a specified field or variable using the pattern provided. The result is an integer output value. The syntax requires two arguments, the field or variable that needs to be observed, followed by the pattern that is being matched, which should be enclosed in double quotes. This function can be used in a search or rule to narrow the data set by placing it in the filtering statement of a search or in the events section of a rule, or it can be used in the outcome section to calculate a statistical function based on the integer output. One example use case for counting substrings is to focus on command switches that may be used by an adversary when multiple commands are being stitched together into a single process launch, and using this to identify anomalous activity. Let's take a look at an example. Let's start with this simple example in search. We've been told that a web page named contact.aspx is suspicious, and there is some concern that it is associated with a web shell. We could search target.process.command line to see if it's referenced. Alternatively, we could use the function strings.count_substring and look for the pattern contact.aspx and return all events where the number of substrings is greater than 0. Let's start by doing that. We can see that there are a few rows returned that reference this pattern one or more times. That said, this might not be the best use of this function, since we could probably write a faster search by just specifying the string we want to match and not add the additional aggregation step that goes along with the count. Looking for more than one instance of the string in the command line would be a better use of this function, which is what we're doing now. In our results, notice we can see contact.aspx referenced more than once as the command line appears to have multiple commands ANDed together. Also take note that we used a function called strings.coalesce that addresses case sensitivity, and in case this is turned on in the search, we can still match for all lowercase patterns against the command line. Let's remove our line of criteria from the filtering statement and use it in a statistical search. This time we can aggregate our process launch events by the hostname variable, which is principal.hostname, and in the outcome section, we're going to count the substrings again for contact.aspx, but this time we're going to output the maximum value, the sum of the substrings, and the command line values that contain contact.aspx. In our results, we can see that work-pacman had a max value of 2, which means that in the command line field, contact.aspx was referenced at most twice. The second value, the sum, is adding up all of the times contact.aspx was referenced in the command line field based on the aggregation of the principal host name and the search time window. Finally, we captured the command lines that contained contacts.aspx for reference as well. Based on this, our next step would likely be to dig into the pacman host for additional investigation. Because we can also use strings.count substring in rules, let's take a look at what that might look like. We're going to leverage the concepts that we applied in search, but this time we're going to count a different substring. The string 2 greater than and 1 may be seen in command lines. Adversaries may use this to redirect standard error to the same destination as standard out, which makes error messages generated by commands get combined with standard out while potentially maintaining stealth. Because it is a common technique, we're going to build a detection that triggers when the number of these substrings exceed a defined threshold within our aggregation window. Our rule looks a good deal like our search. The main change is that instead of searching for the pattern of contact.aspx, we're now looking for 2 greater than and 1. In our rule, we are aggregating by the principal.hostname over a 5-minute window, and in our conditions section, we're expecting more than 15 references in the command line in that 5-minute window to trigger our detection. When we test our rule, we get a detection with a number of events. The benefit of using sum here is that we can put greater weight to the frequency of the value seen rather than the number of events it was in. We can also see the command line values that contain this string to better determine our next steps in our hunt or investigation. The strings.count substrings function provides us the ability to generate an integer value based on the number of substrings found within a string based on the provided pattern, and then apply additional criteria to this value. The syntax requires both the field or the variable as well as the pattern enclosed in quotes. Depending where the function is used, it may require an aggregation function like max or sum to be prepended to it along with an outcome variable, or it could be used in the condition section of a rule as a threshold value. This function can be used in the filtering statement of a search as well, in the event section of a rule, as well as the outcome section. It just depends if this value is designed to filter out data or is part of a computation. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to take a look at 2 string functions that search for patterns in strings and return a Boolean output. These functions can be used as you build searches and rules in Google SecOps. If we had a pattern and wanted to search for it anywhere within the string, we could use the function strings.contains. If we find it, a Boolean value of true is returned. If it isn't, then false is returned. The syntax requires 2 arguments, the field or variable being observed, followed by the pattern that is being matched, which should be enclosed in double quotes. This function can be used in a search or rule to narrow the data set by placing it in the filtering statement of a search or in the event section of a rule, much like the function re.regex. It can also be used in the outcome section. The second function we're going to cover is so similar to strings.contains that it seems silly not to include it here. The strings.starts with outputs a Boolean value as well. The only difference is that it matches a pattern from the start of the field rather than anywhere within the field. Syntactically, it's the same and can also be used in the filtering statement of a search, the event section of a rule, and in the outcome section. With both of these functions, it's a good idea to leverage the functions strings to lower or strings to upper to handle fields and values where there may be case sensitivity concerns. We'll look at some examples that take this into account. Let's start by looking at strings.contains. Perhaps we want to find command line process launch events that contained command.exe/c. This snippet indicates that a command is being executed within a new instance of the command prompt and then is immediately terminated once the command completes. While this can be used for legitimate purposes, a number of command and control platforms will leverage this method when executing commands on a victim system. We can build an initial search like this. The event type and product name focus our search on a subset of events, and we can turn our attention to the target process command line field. Because we don't know where in the field command.exe/c will be, we can use the strings.contains to find this pattern in the field. If we do, this line of criteria returns true. If not, false. Now, we specified a pattern that is all lowercase. What happens if command.exe/c is mixed or all uppercase? We don't want to risk missing any events, so we can add the function strings to lower to our criteria and nest it around the command line so that the value in the command line is converted to all lowercase first, and then the pattern is searched for within the all lowercase string. Now, when we run the search, we can see we're getting results returned. We could stop here, but what if we wanted to refine our search to provide some sort of summarized or aggregated output? We could do this by adding a match section and aggregating on fields like principal hostname and target process command line to get a listing of the unique combinations of host and command that contain command.exe/c within our search window that we could go ahead and investigate and analyze further. Let's shift to the strings.startsWith function. This time, rather than using the function in the filtering statement, we're going to use it in the outcome section and flag command lines that match our pattern as true and those that don't as false. Our filtering statement will focus our search on Microsoft Sysmon process launch events where the command line is not null. We can aggregate our results by the hostname and command line like we did previously. This time we're going to add an outcome section to our search and use the strings.startsWith function to look for command line values starting with the pattern of C users. However, because we are aggregating our search, we need an aggregation function like max, sum, count, or array distinct in our outcome section. Since max, sum, and count are all for numeric aggregations, let's use array distinct. Notice we get an error now that says expect type enum int float string got type boolean. This is because our function outputs a boolean value, not a string or any of the other types. We can still use the boolean output in the outcome section by adding a conditional or if then else statement right here. Now, we're converting the command line to all lowercase and finding the pattern of C users at the start. And if that is true, then we'll output the string true, and if not, we will output the string false. With that change, we're in good shape. We're going to go ahead and sort the true strings to the top and limit our output, and then run our search. In our results, we can see that we have a subset of command lines that were run from the C users folder, marked true, and those events that did not start with C users are marked false. Could we have filtered the non-C users in the filtering statement instead? Sure. But sometimes when hunting or even just exploring our data, we want to go ahead and extract a broad set of data and apply a flag that might allow us to look more broadly and then refine our search further. Both of these searches could be adapted to rules. Let's take our last search and create a detection when executables are triggered from the users folder. Here we have moved our strings.startsWith function to the event section, and for our rule, we're aggregating by the host name over a 1-hour time window. If we get a detection on user execution in the C users folder, we want to generate an aggregated count of events that met this criteria during our 1-hour time window. We also want the names of the users who launched these processes. And finally, we want to get the first folder after C users in the events. Because strings.contains and strings.startsWith output a Boolean value, we can't use these functions to output the folder name. Instead, we could use a function like re.recapture to extract that value from the command line and display it in the user folder outcome variable. In our results, we can see that many of the process launch events were executed by Dan Cooper out of the C users public folder, which could be suspicious. We can also see that during a different hour window that Dan also executed processes from his personal folder as well as public. If the public folder under users is not used in the organization, that would probably be something to investigate further. The functions strings.contains and strings.startsWith provide us the ability to match against a provided pattern either at the start of the field or variable or anywhere else within it. Either way, the function will provide a Boolean output. To use these functions, we require the field or variable followed by the pattern in double quotes. The functions strings to lower or strings to upper can be nice tools to use to ensure pattern matching in fields where values could be mixed case. Finally, this function can also be used in the filtering statement of a search, the events section of a rule, as well as in the outcomes section. Though remember, in the outcomes section, an aggregated function like max, count, array distinct is needed when aggregating events. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Chronicle. I'm John Stoner, and today we're going to use the string function concatenation in a YARA-L rule. While string matching and regular expressions can provide a good deal of flexibility, there are cases where additional capabilities are needed. Chronicle provides a set of functions that can be used for building YARA-L rules. Today we're going to focus on a string function for concatenation. The concatenation function takes n number of arguments and returns a string with these values in a single field or variable. Strings.concat provides a method to take strings, integers, floats from UDM, as well as constants to create a value that can be used in a rule. Strings.concat can be used in the outcomes section to gather values into a single field, but can also be used in the events and match section. Today we'll demonstrate these examples along with using it as a match variable in our rule. To highlight a few different ways that we can use the function strings.concat, we have a starter rule here that is looking for file events from our Zeek sensor. We've refined our data set to just HTTP events where the principal IP address has a 10 dot address. We're going to start off by not having a match variable to aggregate over a specific time, but we'll add that shortly. With our defined criteria, we have 4 detections during our test window. I realize this isn't a very exciting rule, but our focus here is how we can use the concat function in the context of any rule, so stick with me. A common question is, how do I concatenate an IP address and port? IP addresses in UDM are stored as strings and ports are stored as integers. Strings.concat can easily put these fields together. Now, before we start celebrating how easy that was, I should mention that an IP address field is a repeating field, so that does add a little complexity. We can handle repeated value fields in a few ways depending on the use case, and if the function is being used in the outcome or event section of our rule. Let's walk through a few different scenarios. We'll start by defining the first value in the repeated field of target.ip to be our target_IP placeholder variable. Placeholder variables and UDM field names can both be used in outcomes, so let's start by putting them both together within our function. When we test our rule, we can see that we have the outcome variable of IP_port populated with a concatenation of these values, and we can see the 2 columns for target.ip and target.port displayed as well. The only problem I can see with this is that my IP address and port are jammed together, making it difficult to read. To resolve this, we could add a constant like a space between the 2 fields within our function. Notice that we enclose our constant with double quotes. When we test this, notice we have a little bit of daylight between the IP and port. Let's refine this a bit further to be a little more descriptive by adding a constant in front of the IP address as well as a / and the word port in front of port. All right, that looks much better. What happens if we want to add a match section to our rule so that we can aggregate by our principal IP address? Notice that when we add our match section and match variable of principal_IP, our outcome variable is no longer valid. The error message that we get is that event values in a match window must be aggregated. We can resolve this by adding the aggregation function of array_distinct around our outcome variable. This time, notice we get 2 detections based on our time window. Notice that our aggregated outcome variables are shown in the detection, and when we expand the detections, we can see the events with their respective target.ip and target.port values. Hopefully that provides a nice set of examples of how strings.concat can be used with outcome variables. Now, let's highlight an example of how strings.concat can be used in the events and match section. Rather than grouping our detection on the principal IP, we're going to aggregate our detections by the target.ip and port. To do this, we can use strings.concat in the events section and save this value to a placeholder variable. That placeholder variable can then be used as a match variable in the match section to aggregate values over a time window. This is just like any other match variable we have previously built, but this time it is based on two values concatenated together with a / thrown in to separate the IP and port. In our results, we can see that match variable in our detection. One final thought as we wrap up this demonstration of the strings.concat function. Throughout this demonstration, we use the first value in the repeated field for target_IP by specifying a placeholder variable or target_IP for the field network.target.IP (0), close square bracket. What if we didn't care about the specificity of the repeated value of the target IP? What if we just said, give me all the values that exist for target IP? Well, we could just prepend the array_distinct aggregation function to our strings.concat function. The important point here is that we would need to use the array_distinct for the rule, whether or not it had a match section in it. We covered a lot of ground here, and there's even more use cases for strings.concat. In fact, I'm holding back one of these for when we get to reference lists, so make sure you keep checking back with us. Remember that string, integer, and float fields can all be used in the strings.concat function. Couple these with constants and we can generate some descriptive string values. Using the function is easy, we just need to separate the fields and constants with commas. And remember, the constants need to be enclosed in quotes. Placeholder variables and UDM field names can be used as well. Finally, we use strings.concat in the outcome section to describe values within our detection, but we also use it in the events section to create a placeholder variable and a match variable as well. There are lots of ways to use this function. Just be mindful of repeated values in fields as you develop your rules. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Chronicle. I'm John Stoner, and today we're going to use the string function coalesce in a YARA-L rule. The strings.coalesce function returns the value of the first value in the function that does not contain an empty string. Coalesce can work with string values as well as with constants. The syntax for coalesce is strings.coalesce followed by the field or constants of interest. The coalesce function can be used in a number of different ways, but today we're going to use it as an aggregation that we can use for our match variable. Because the success of coalesce is dependent upon working through a set of values and finding one that isn't null to use in our rule, it makes sense to start with a search to show the fields we have available to work with in our rule. Here we have the search criteria that we will be using to develop our rule. We can see that we have file events from our Zeek sensor that use the HTTP protocol and have a principal IP address that starts with 10. In our results, we can see that we have a principal hostname and principal IP as well as a target IP, but no values for the field target hostname. If we look in our event viewer, which is sorted in alphabetical order by field, we don't see target hostname either. Let's take this criteria and apply it to our rule. Here is our YARA rule. I will admit we aren't building a really wild detection today, but we are focusing on a tool that will help build better detections. I promise you that. Notice that in the events section, we brought all of our criteria from the search. To this event section, we added a placeholder variable for principal hostname that we then used in our match section to aggregate our detections. Let's use the principal hostname field as a match variable and aggregate our results over a 5-minute window and test our rule over that same time range we used in our search. All right, that test returned 12 detections with one or more events in each of our detections. Now, suppose we want to group our detections not by the principal, but by the target. This isn't unreasonable. Perhaps we want to understand how many events are associated with a specific target or destination. Let's group by the target hostname just like we did with the principal hostname. We can change our placeholder variable and then update the match section like this. Now, when we test our rule, we get a message of no detections found. This is because the target hostname field is null, as we saw in our search, and we can't match or aggregate on a field and value that doesn't exist. So the detection returns 0 events. That's not great. We don't want our detections not triggering because a field isn't populated for any reason. How can we mitigate this? Well, we can use the strings.coalesce function to create a placeholder variable that can be used as our match variable that would attempt to find a non-null value to use. In the event section, we can call our function and we will include the target.hostname and target.ip in the function. Now, we already know in this example that the hostname does not exist, but perhaps we always want to set an order of precedence. For example, hostname, IP, MAC. We can then take our placeholder variable called $target_match and use that as our match variable and group over 5 minutes. When we test our rule, we get 12 detections and the target_match is the IP address for each one. This isn't a surprise since we know that the target.hostname didn't exist for any of these events. Let's run this one more time. This time, let's remove the requirement that the principal.ip must start with the 10. Address by commenting out of the rule. When we test, we can see the target match in some cases is the target hostname of WinADFS and other times is the target IP address. Coalesce provides the flexibility and helps us identify and aggregate all of the events meeting our criteria above. Remember, when working with the strings.coalesce function, that it's used with string fields and constants and will return the first non-null value, so the order of the values is important to consider. The syntax is very straightforward. Just order your n number of values carefully. While we only focused on using coalesce in the events and match sections, it can also be used with the outcome section as well. We only focused on a specific example with network-centric events, but this can be applied more broadly to a user, or even a user or asset or cloud resource. The most important thing here is to determine which values are the most important and put those first within the function. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site, and we are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to take what we previously learned with statistical searches a bit further and look at additional aggregation functions and calculations that can be performed in UDM search to ask more complex questions of your data. We already discussed that statistical search is an expansion that goes beyond the tabular results set into aggregated data by common values and generating calculated values. This time we are going to use additional concepts like placeholder variables, aggregation functions, and mathematical operators that are part of YARA-L and apply them to our statistical search. If you've written YARA-L rules, some of these concepts may be familiar to you. As we build our search, you may look at how I built it and think there might be a different way to go ahead and approach this problem, and chances are you're probably right. There isn't a single way to achieve the same outcome, But we're going to show one method today, and you may uncover additional methods that you want to use, and that's great. Finally, there are a number of other YARA-L functions available to work with data, and we'll use a few of them today. Just know that there are additional capabilities that can be used when working with your data set. We're going to start where we left off in our previous video with Corelight TCP network connection events. This time, we want to generate a listing of the top IP pairs based on event count. One approach we could use would be to add both the principal IP and target IP fields to the match section. I'm going to use a placeholder variable called IP pair and the strings.concat function to combine these values into a single variable with a pipe to separate the two values. Additionally, my data has an annoying IPv6 address of : :1 on one of the servers. So after creating this placeholder variable, I'm going to exclude IP pair values that have this value in the field. From there, we can match on this new placeholder variable, and then, like we've done previously, generate an event count, sort by the count, and limit our results to 10 rows and run our search. Our results are the IP pair in the match section and the count from the outcome section. Now, let's use another aggregation function with our results. The aggregation function of sum will take all of the values in a field and add them up based on the aggregation value, in this case, our IP pair. We can add the sum of the sent bytes and another sum for the received bytes to our outcome section. Let's also adjust the order section to sort by the sum of the received bytes. Now in our results, we have 4 columns: the IP pair, the number of events that match this IP pair, and the sum of the sent and the sum of the received bytes between these two IP addresses. This is looking pretty good, but perhaps we want to add some sort of explanation for each row to denote something about our data, like, is this an internal only or includes external addresses? We could use the net.ipInRange_CIDR function to look at the IP address and return a Boolean value if the field matches the CIDR block provided. Because we have aggregated our result set, we need an aggregation function in front of our conditional statement, that is, the if-then-else statement. So we can prepend this entire statement with the aggregation function of array_distinct. In this case, if the principal and target IP addresses are both part of the provided net block, we want to go ahead and return internal only, and if not, we will return external. This provides us a nice summary of each pair with some key values. If we wanted to refine this further to provide additional granularity on the data flow, we could do that as well. While there is a directionality field in UDM, let's build our own to indicate if data is flowing between two internal addresses, or from outside to inside, or from inside to outside. This time, we have multiple conditional statements nested within one another. That is, if this, then that, else a new if statement, and so forth. When we run our search, notice our descriptive column now displays a few different outputs depending on the IP pair values. I realized I used the net_ipInRange_CIDR function in the last two examples of this search. And some of you may be asking, yes, but what if I have a number of IP ranges I want to include in this search, and they are non-contiguous? Could I do something similar? The answer is yes, with CIDR lists. We could construct a similar nested conditional statement using AND as well as NOT with the in_CIDR netBlockList functionality. Notice that, like our previous examples, our conditional statements are nested within the aggregation function array_distinct. When we run our search, we get a similar result, but we are able to use more net blocks within our search. In our demonstration, we've highlighted how we can add placeholder variables and aggregation functions like array_distinct and sum to our search. It's also important to remember that there are multiple ways to achieve the same result, so there is not a single right or wrong method. It really goes back to what you're trying to accomplish. Finally, while we just use strings.concat and net IP in range CIDR, there are a number of additional functions that YARA-L makes available to us that can be used in search. Conditional statements, like if then else, can also be used, as well as mathematical operators within the outcomes section of our statistical search. In future videos, we'll be digging into more functionality, see what I did there, that is available to users in both search and rules, and we will be building some of these examples using statistical search to highlight the capabilities. I hope you'll check them out. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to introduce the statistical search capability that extends UDM search to ask more complex questions of your data. Statistical search is an expansion of search that goes beyond the tabular result set that we get when we specify fields and values. With statistical search, the analyst has the opportunity to aggregate data by common values and generate calculated values while applying sorting and limits on the result set. In an effort to more tightly align search and rules, Google SecOps utilized YARA-L constructs for statistical search so common groups like match and outcome will look familiar to those who write YARA-L rules. Even if you're not familiar with these constructs, this video will break these constructs down. Finally, it's important to note that while any field in UDM can be used in a search, when we get to the point where we are aggregating and calculating values, only the fields that are referenced in the match and outcome sections are the fields or variables that are going to be used in the results of your statistical search. We'll walk through all of this by looking at some real-world examples, so with that brief introduction, let's dive in. Our search screen has the results of a search for network connections from Corelight in it. We'll be referring to this search string as the filtering statement, as it takes all of the UDM data and reduces it to a subset. While we could use the aggregation section on the left side of the page to view distinct values and counts of individual fields, we really want to roll this information directly into our search so that we can save the search and use it for other purposes. Let's say we wanted to get a feel for the possible values that reside in the metadata product event type field. In Corelight or Zeek, this field is populated with different types of network activity. We can generate a list of unique values by adding a match section to our search. The filtering statement doesn't change, we just add a match section and the field or fields we want to aggregate against. It's worth mentioning that unlike in a YARA-L rule, the match section in a search can accept either a variable defined in the filtering statement or a UDM field name. Here we can see that for the time window in the search, we have a few different network types in our result set. You may be thinking that's fine, but I can see that in the aggregation section of search. Let's add another dimension to our match section and specify another field. Now we are looking for a listing of all combinations of metadata product event type and network IP protocol. We can see that all of the events, with the exception of the connection log, have an IP protocol of TCP, where the connection log has ICMP, TCP, and UDP data contained in it. Perhaps we want to quantify these values. We can do this by adding an outcome section to our rule and adding an outcome variable like this. My outcome variable is called event_count, and we are counting the values in the field metadata event type. There are any number of fields that we could count against, but every field has a metadata event type in it, so I'm going to use that. Now, we have a listing of results, but they aren't in any particular order. Let's resolve that by adding an order section to our search. We can use fields and variables from the match and outcome section to sort our result set, and we can specify the sort order as well. Here we are sorting by the number of events in descending order, followed by the IP protocol in ascending order. Each sort value is separated by a comma, and if ascending and descending are not specified, the sort will default to ascending. Let's refine our search slightly by limiting our result set. Perhaps we only want the top n values in our search to be returned. We can add a limit section to our search that after the sort is applied will only return the number of rows specified within the limit section. Here we can see that we have the top 3 rows returned, and we have counts for each of the combinations of network types and IP protocols in our dataset for the time range specified. What if we had a filtering statement and we just wanted to generate some calculations on that filtering statement without any additional aggregation? We could do that as well. Let's add the product event type and IP protocol to our search, remove the match, order, and limit sections, and output the event count for the filtering statement alone. When we run our search, we get a single value, which is the event count based on the filtering statement requested. Google SecOps has expanded the search functionality to perform statistical search that can aggregate results on common values and generate calculations, like a count for users. Statistical search uses YARA-L constructs for this syntax, with the match section used for aggregations and outcome section used for calculations. Additional sections like order and limit are available for sorting and outputting a fixed number of results. Finally, it's worth remembering that a statistical search can have a match section, an outcome section, or both, depending on the type of search being built. There's a lot more coming, and in the future videos, we'll highlight additional functionality available to users, and we'll use statistical searches to highlight these functions. How's that for some foreshadowing? If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the adoption engineering team at Google Cloud, and today we are going to build a single event rule using string matches. In previous videos, we have touched on the structure of the rule, operators, and variables, so this is an opportunity to put these pieces all together. For a single event rule, we need a minimum of 3 sections: meta, events, and condition. We need to identify the relevant fields in UDM to use in our rule logic, and then we need to add values in the form of strings against those fields. Because we are using strings, these values will be enclosed in double quotes. Because this is the first rule we are creating, we are going to use this as a simple example. Let's create a rule that would detect the use of who am I. To do this, we can click New in the top left corner of the rule editor. Chronicle presents us with a rule template that we can modify and use as we see fit. Let's start by naming our rule something meaningful, like who am I _process creation. From there, we can add as much or as little to our meta section as we'd like. If you take a look at the community rules in our GitHub repository, you will see a standard set of metadata that we use for our rules to ensure that it is as descriptive as possible. I'm going to paste in a set of fields and values that I feel describe this rule, but you can adjust this however you see fit. Our events section contains the fields and values that we can identify are events of interest. A good practice is to use the UDM search to identify events of interest using the tabular views, and then take those fields and values and use them in our YARA-L rule. In our case, we can see in our search that the metadata.events_type of process launch and our target.process_command_line of who am I are the values we need to detect this activity. In our rules, we need an event variable, so let's use something descriptive like $process. Keep in mind that because the field values are on separate lines, these two pieces of criteria are ANDed together, but you could place an AND between them as well if you wanted. Also remember that we have the no-case modifier, and while it does not work with the enumerated fields like metadata.eventType, it is generally considered a best practice to use against fields like command line, particularly on Windows systems where upper, lower, and mixed case can be used to execute the same program. The last section we need is the condition section. In our rule, we need to ensure that we capture the event variables that are needed for this event to fire, or a threshold using the pound value. In this case, there isn't much to do here. We just need to include the event variable which we defined earlier as $process. With that, let's go ahead and test our rule and see if we get the detections we expected. Since we did, let's go ahead and save our rule. Remember, when you start building rules, the meta, events, and condition sections are always included. UDM search is often a good place to view events and their fields and value as you explore your data. And when building your criteria, use double quotes for string values. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the adoption engineering team at Google Cloud, and today we're going to build a single event rule using a regular expression. Previously, we discussed the key sections in a rule, so think of this as a natural extension to our string matching video. Chronicle uses Google's RE2 software library for regular expressions. It is similar to other regular expression libraries in terms of syntax, which lowers the learning curve for use with Chronicle. It can be used in a few different ways in YARA-L. While there is a function for regular expression matching today, we are going to use the / notation, which can also be used in UDM search, but in future videos, we will discuss the function as well. In case you're wondering, why might I need or want to use a regular expression in my rules? The best example I can provide to you is that any field that a user can input values into is a good candidate for a regular expression. In fact, in our example today, we're going to look at using regex with values from a command line where obviously there can be a tremendous amount of variability. To illustrate this, here are a series of Windows admin shares that connect to $, admin $, and IPC $ from one system to another. As we can see, the net use command could use mixed case, have additional spaces, map to any drive letter, map to any of these three shares, or contain a prepended path to the net use command. All of these permutations make string matching extremely difficult. However, this can easily be solved with a regular expression. Let's take a look. We're going to build a rule that detects when Windows administrative shares are launched using the net command based on our previous slide. The use of these shares aligns with the MITRE ATT&CK technique remote services and the sub-technique SMB Windows admin shares, which is part of the tactic lateral movement. We're going to include these descriptors in the meta section of our rule so other users can better understand what our rule is detecting and providing coverage for. Now, as we start building our regular expression in our rule, we need to think about the key values that we can use in our criteria versus the values that might have more variability. Let's start by clicking the Create Rule button in the Rule Editor in the top left corner of the screen. Chronicle will present us with a rule template. Let's start by naming our rule T1021_002_admin_shares, since T1021.002 is the attack technique ID. Because we want our rule to be easily understood by others, I'm going to paste the metadata into the meta section of the rule. In the event section, we'll start by adding the enumerated value for metadata.event_type of process launch to focus our rule on a subset of our events. From there, I'm going to inspect the target.process.command_line field for values that would indicate the creation of Windows admin shares. Based on what we discussed previously, some common values when creating a Windows admin share would include the net command, the use option, as well as the share names $, admin $, and IPC $. The path, the drive letter, and the server values are all variable, so including them in the regex statement would not be ideal unless we were focused on a very specific subset of systems. Regex statements can use the / to start their match, which is where we will start. Because net may or may not be the first character of the command line, we will just start with NET. If we wanted to force NET to be the first characters in the field, we would start our expression with a caret. By just starting our expression with net, RE2 will find that pattern anywhere within our field and match from there. Now let's talk about wildcards for a moment. Because net use could contain net.exe use or net space use and still be valid, we can enter $* between the words net and use to basically say find the pattern net and then find anything until we get to use. We could also use parentheses and pipes to separate values and compare each one with an OR statement between them. So when we see parentheses C, pipe, admin, pipe, IPC, close parenthesis, this means C or admin or IPC. The $sign after the parentheses would be appended to the values in the OR statement, so we end up looking for C $, or admin $, or IPC $. Don't forget that some characters, like the $, have special meaning in regex, which is why we would prepend to the $, an escape character of /. Because we have the /$ it would then be treated as an actual $, and not the end of an input. And of course, we want to add the no case modifier to the end of our criteria. We could force case using RE2, but the no case modifier is so easy to use, why not use it? The last section we need is this condition section. In this example, we just need to include the event variable which we defined earlier, and that would be $process. With that, let's test our rule and see if we get the detections we expected. Notice that we have detected target.process.command_line with different drive letters and different shares. With our regex statement, this is much easier to do. Once we are happy with our logic, let's go ahead and save our rule. Remember that when it comes to using regular expressions and rules, that the RE2 syntax can be leveraged to streamline your detection. The rule criteria can be set to use regex by wrapping your values in /, and don't forget to use the no case modifier. Finally, any field that leverages user inputs is a great place to consider using regex. This isn't an absolute by any stretch, but definitely a good place to start. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the Adoption Engineering team at Google Cloud, and today we're going to talk about the options available when creating and editing rules. For each rule, we have a number of options available to us. At a high level, these include turning the rule on or off, when we run the rule, and the version of the rule we have available to us. Let's look at these concepts and how they apply to a rule. Now, in the top right corner of our rules pane, we can see 3 dots just under the View Rule Detections button. When we click on these dots, we can see a listing of rule options. It's important to understand that the rule options you see here are specific to the rule in the pane. We have the rule Windows Event Log Cleared selected, and based on the options, we can see that the rule is not live. That is, for every new event coming into Chronicle, we are not applying this logic against those events. Notice we are also not alerting. If we had alerting turned on, detections associated with this rule would appear in the Alerts and IOC page, like this. Live and alerting rules mean that the analysts would be triaging these alerts as they are identified. We can activate these options by flipping the switch next to each option, like this. You may be wondering why we would have alerting turned on, but not a live rule, or vice versa. The reason is that there may be rules that are being tested or hunting rules that we want to collect detections against and analyze, but we don't want them to appear in the alert queue for our analysts to triage. Conversely, we might want to run a retro hunt using a specific rule and generate an alert against historical data, but not use the rule against new data. Now, when it comes to hunting a rule, we can set our rule to run at a specific frequency, 10 minutes, 1 hour, or 24 hours. As just mentioned, we can also perform a retro hunt to run our rule against historical data. This can be incredibly helpful when new logic has been added to Chronicle that you want to use against older data. From a versioning perspective, we can duplicate our rule, so if you wanted to use it as a template for a new rule, we can. We can also view the detections a specific rule has triggered, which has the same capability as the button at the top of the page. The View Versions option allows us to view and compare versions of the rule and save them so if logic changes over time, we can easily understand the differences between them. Lastly, we can archive a rule if we no longer want the rule to be used against live or historical data. Archiving the rule does not delete it, however. The options provided in the rule engine allow us to control whether a rule is being applied against our live data and if an alert is generated on the match. It also provides us the ability to define the frequency a rule is run and if it is run against historical data, and if so, what span of time should it consider. These options also allow us to compare versions of the rule that have been saved over time, make copies of rules for other uses, as well as archive rules that are no longer needed. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the adoption engineering team at Google Cloud, and today we're going to learn how we can set thresholds on our rules. Previously, we introduced the condition section of YARA-L as a mandatory section for every rule. However, in our initial rules, the only thing in our condition section was the event variable for the criteria in the event section. Basically, if the criteria exists, trigger the rule. However, as we get into using multiple events to evaluate our rules, we can start counting events that meet our criteria, and if the number of events or fields exceed a defined threshold, we can trigger the rule. We can use outcome variables in our condition section as well, but we're going to save that for another time. To demonstrate how these thresholds in condition can be used to trigger a rule, let's use an example with failed logins. It's safe to assume that everyone has generated a failed login event at least once in their life. We forget our password, we mistype something, no problems there. However, if an individual user generates too many failed logins, perhaps that isn't someone who just came back from vacation and is just getting settled back in, but an adversary attempting to gain access to an account. Let's trigger a rule to address this concern. Here we have a starter rule that is looking for failed Windows login events with a specific event code of 4625. We have a match section to aggregate our events by user ID over a 5-minute window, so we don't get a detection for every failed login attempt. So that's great. However, when we test our rule, we still end up with a bunch of detections, and they seem to vary on the number of failed logins in that 5-minute period. Perhaps for this specific rule, we want to only be alerted when a certain number of events have occurred, more than 5 failed events perhaps. To do this, we can modify the condition section of our rule and change the condition from $fail, which basically means do we have an event variable that meets our criteria, to fail greater than or equals to 6, let's say, which means we're going to count the number of events that meet the criteria in the event section that have our specific event variable associated with it. And if that count exceeds our threshold, 6 or more, trigger our rule. And when we run our rule, we can see that our overall number of detections have dropped. We use the test rule, as you can see there, to make that happen. Another way that this count within a condition can be used is to trigger a rule based on a distinct count of a specific value within a field. And if that threshold is met, trigger your rule. This time, we're going to go ahead and change our rule a bit and add in a second placeholder variable for principal.hostname. We're going to group our failed events by this host name over the course of 5 minutes. But this time, we're going to take the placeholder variable for target.user.userid and count the number of unique values in that specific field, meaning the unique usernames. While we haven't touched on the outcome section and its variables, I've gone ahead and added one outcome variable that we can see the array of the users that are part of our detection. The first time we test this rule, we're going to specify our condition as hash target_user is greater than 0, which is basically saying if we have one or more usernames in our failed event logs, trigger the rule. Not surprising, we should see plenty of these. So when we run our rule and test it, we can see that we have 11 detections, and that our first detection has 6 supporting events with it, but only a single user, frank.coalesce, in it. Our next detection has a number of distinct users, including Frank. This is because the window of events was set for 5 minutes, and the first detection window completed with just Frank meeting that criteria, and the next detection window had a number of other users associated with it. Now, let's modify our rule to only detect when we have more than 10 distinct users within a detection window on the same host. And when we test this rule, notice that we only have 6 detections overall, and using that outcome variable, we can see that we have a list of usernames that had failed logins to a specific host in a 5-minute window. Now, we'll get further into outcome variables and building our conditions a little bit later, but hopefully these examples illustrate some of the possibilities that the condition section can provide to detection engineers. Now remember, as you start building rules that leverage thresholds in the conditions section, you can generate these counts based on the number of events seen or number of unique values. Now, we didn't cover this, but in fact, you could build a rule based on both. The conditions section can accept event or placeholder variables, but not UDM fields. Yes, they will support outcome variables too, but that's for another day. Finally, thresholds with conditions are used with rules that are evaluating multiple events and are being grouped by one or more values in the match section. After all, how can we decide if a threshold is exceeded without grouping events together? If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more, and don't forget to engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the adoption engineering team at Google Cloud, and today we are going to talk about navigating the rules editor. With the rules editor, we can apply sorting and filtering to view the rules that we have available to us, view the history of detections for a specific rule, as well as test a rule to ensure that it is behaving as we would expect. Let's take a look at each one of these capabilities. When we first open the rule editor, we are presented with a list of rules that are in the system. This listing can be filtered by active or archived rules, or both. For a detection to be generated, a rule must be active. Our list of rules can be sorted alphabetically, or reverse alpha, or by last updated. To view a specific rule, click on that rule. In our case, we are selecting the rule Windows Event Log Cleared. In the right pane, the rule logic is displayed. To view the detections associated with this rule, click on the button in the top right corner with the name View Rule Detections. This will open a new dashboard with a list of detections associated with this rule, as well as metadata and what retro hunts, if any, have been run against the rule. At the bottom of the screen, under the rule, is the test rule results section. Oftentimes, before a rule is fielded, it is a wise idea to test your rule against your dataset to ensure that your rule logic aligns with what you're looking for, assuming you have the data. By default, the test rules can run against a 2-week block of data. Select the time range of interest and click Run Test. This test applies the rule logic against the time frame selected and returns detections. This provides you the opportunity to assess the rule before making it live and generating alerts that your security operations team has to triage and respond to. As you start navigating the rules editor, remember that the sort and filter will help you find the rules you want to edit or test, and that the View Rule Detections will show you detections that this rule has previously identified. The test rule capability provides a method to validate the rule before fielding it without creating any noise for your analysts to deal with. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site, and we are continually adding more. And don't forget to engage us on the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to introduce a regular expression function called re.replace. re.replace provides a method to replace a portion of a value with another value, which can help finesse data for YARA-L rules and search to work with. re.replace works in concert with other functions and placeholders and can be used to adjust values in fields that can then be compared to other events or lists. The syntax for the function contains 3 arguments: the string, which is often a UDM field, the regular expression that is being matched, and the replacement value. Let's take a look at it in action. Our example rule picks up where we left in our previous video on strings base64 decode. Let's start by looking at our hostname field. Notice that it is a fully qualified domain name, but suppose we wanted to join this value to a field with a host name, not the full domain name. Or we wanted to use a reference list, but that reference list doesn't contain fully qualified domain names either. We could use the re.replace function with our principal hostname field and supply our domain .stackpads.local to match on, and then replace it with a null value. This writes to the $hostname placeholder variable everything before the domain name. When we test our rule, we can see that our detections that meet this criteria are now just aggregated by the hostname and not the fully qualified domain name. Let's apply this concept to a list. As you can see in our list, we have a set of host names, not domains. If we wanted our rule to apply to only those hosts that matched, we can use a list and match that hostname placeholder that we just used with the re.replace function. Heck, we could go ahead and collapse that into one line if we wanted. When we test that, we only get the detections of host names on that list. So far, so good? Let's move to our decoded PowerShell. As you can see in the decoded PowerShell, we see invoke web request calls that are going out to a URI and downloading a file. Perhaps we want to know when folks are issuing commands to this function. We can take our decoded PowerShell and compare it to the string using regex, or can we? When we test our rule, we don't get any detections back. Why is that? Well, this was a bit of a setup. Let me take the encoded PowerShell and paste it into CyberChef, and we can convert it there. Notice how there are dots between each value. If we follow that pattern in our rule, we could add dots between each value and try our rule again. This time we get a hit. However, who wants those dots in there? The reason they are there is that there are null bytes being represented in the output. To remove them from our decoded PowerShell, we can use re.replace with this /0 and replace it with a null. Once we do this, we can do a comparison for invoke-web request with no dots, and we get detection matches. That's a bunch of examples we just threw at you, but this is where we can pull all of the regular expression functions, lists, and string functions in previous videos together to show the capabilities that we have in YARA-L rules and search. As you can see, re.replace allows us to swap a portion of a field's value for another value and then use it elsewhere in our YARA-L rule or search. We could even null out a portion of a field, like strip off the domain from an email address to return just the username. The output can be written to a placeholder or outcome variable and can be nested with other functions, providing a whole world of flexibility when working with these values. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to introduce a regular expression function to match portions of values within fields that can be applied to both rules in YARA-L as well as search. The function re.regex uses re2 and is equivalent to enclosing a string in forward slashes. In fact, we introduced this concept early in our video series, but now we are going to revisit its functional equivalent. The syntax for this function is re.regex followed by the field we are looking within and the re2 expression that we are matching on. The re2 expression will be enclosed in backticks. re.regex is a great way to identify values of interest, particularly in fields that contain user-inputted values or places where folder structures reside and there's some variability. re.regex by itself is not used with a placeholder or outcome variable. It returns a Boolean value. Let's take a look at it in action. Our example rule is detecting process launch events that have a target process command line value that contains a user input of netuse followed by a few different window shares, $, IPC$, and admin$. The first time we run our rule, we are going to use the syntax field equals / followed by our re2 expression and closed out with another /. Notice when we test the rule, we get 8 detections, and we can see the command line values in our results. Let's change our regular expression to use the equivalent re.regex function to perform the same task. Notice this time we do not have field equals value, but the field and expression within parentheses. The regex is enclosed in backticks, and when we test it, we get the same detections as we did in the previous test. Both methods that use regular expressions are valid. It's up to you to decide which one you want to use. Now, it's worth noting that when using the / around the re2 expression, that we need to escape any forward slashes in our expression with a backslash. Whereas with the re.regex function, because it is encapsulated in backticks, we don't. So, if we wanted to look for netuse commands that have a /delete switch, we would first need to add a backslash before our forward slash that accompanies the delete switch. Notice when we test our rule, we get 4 detections. Now, when we swap this for our re.regex expression, we don't need that escape character, and when we test, we again get 4 detections. All right, we also mentioned that re.regex can be nested. Let's take our rule and add an outcome statement. We will keep our original regex statement in the event section the same, that is, looking for all 3 window shares that are called from netuse. This time, we will add an outcome statement that marks the events with the admin $ as yes and the others as no. In this example, we are using if then else and nesting the regex function and evaluation within the outcome. When we test this rule, we get the same 8 detections we saw before, but now we have an outcome variable that contains the values yes or no, depending upon the contents of the re.regex function. We could then take that outcome variable and add it to our condition section if we wanted to further narrow the alerts we receive. As you can see, re.regex can be used in the same way as UDM field equals /value /. It returns a Boolean value and uses re2 syntax. It can be nested within an if-then-else statement and is most often used where fields have variability due to user input or folder structures, but it can be used elsewhere as well. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to introduce the use of reference lists to our YARA-L rules. Reference lists provide an easy way to identify multiple values within a single field for a rule without having to build an OR statement. For example, if there were 5 IP addresses we wanted to find, writing field equals value 1 or field equals value 2 and so on would get pretty tedious. Instead, we can build a reference list, add the values of interest, and simply use the syntax of field in %, which tells us that we are going to use a reference list followed by the name of the reference list. Today, we're going to use a string reference list, which is case sensitive. In future videos, we'll cover additional reference list types, including regex and CIDR. Let's take a look at how we can use reference lists. We're going to build a rule that detects core-light network connections that originate outside our defined net block of 10.128.0.0/24 and connect into it. We are excluding ICMP events, and we are grouping our detections by the principal IP address over a 30-minute window. In the outcome section, we're generating a count of the number of events within each detection to determine how many events are occurring within our match window. When we test our rule, we can see we have 73 detections, with a number of detections having numerous connection events associated with these external IP addresses. Let's look at how we could use a string reference list to help us in our rule. Perhaps we've been running this type of rule, and over time, we've been researching these different IP addresses and determined that some of them are suspicious and some of them are totally legitimate. While we could write an OR statement with all of the IPs that we have determined are suspicious, that would be onerous and would have to be replicated in other searches or rules. Instead, we can create a reference list, in this case called suspicious IP list, and add our IPs to that list. We've already added a few IP addresses from our result set to this list to demonstrate how a list like this can be used in a rule. Notice how we can also add a comment to a value by using 2 /, just like we do in a YARA-L rule. When we test our rule now, we are only getting detections that match the principal.ip field to IP addresses on the list. If we wanted to generate detections based on values not on our list, we could easily add the operator not to the beginning of our line and return those events as detections instead. So far, so good? A common response we get is, that's great, but we want to build a rule around a suspicious port list. Can we do that? The answer is yes, but there's a slight twist. Because ports are stored as numeric fields in UDM, and this reference list is a string, we would get a type mismatch error if we add this criteria to our rule in the same manner we did our IP address. To solve this, we can convert this numeric value in the port field to a string by using the function strings.concat and appending a null value to the end of our target.port. Our result is that our port numbers are now evaluated as strings that can be compared to our string reference list of suspicious ports. For readability's sake, we added an array distinct aggregation function to our outcome variable called ports and added it to our results so we can more easily see our results. If we wanted to apply this same kind of rule but to internal traffic, we could remove the not statement from our principal IP address, and this time we can see connections over 135 and 445 for our internal IP address pairs, but not port 25 or 21 traffic. During our demonstration, we highlighted how we can use string reference lists to easily find multiple values within a field without writing a large OR statement. The syntax for this is the UDM field name followed by in, a %, and the list name. This syntax can also be used in search, and these reference lists can be reused in multiple rules, making them nice and portable. While we only covered the string reference list today, there are additional CIDR and regex options that we will explore in future videos that provide additional flexibility depending upon the detection rule. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to introduce the use of regex reference lists to our YARA-L rules. Regex reference lists, much like our other reference lists, provide an easy way to identify multiple values within a single field for a rule without having to build an OR statement. With regex reference lists, we're not limited to direct string matches. This can be incredibly handy when working with file paths, command lines, and other values that we need a portion of the value to match rather than the entire value. Regex reference lists use RE2 syntax, which is used throughout search and rules in Google SecOps. Chances are you're already using it. The only difference in the syntax for regex reference list is that the word regex is inserted before the reference list, so our syntax will be the field name in regex, %, and the name of the reference list being called. Let's take a look now how we can use this in our rule. Our example rule is going to detect process launch events from Microsoft Sysmon for hosts in our domain. Because we are going to look at the data in the field target process file full path, we are going to require that this field is not null, so we don't end up with extraneous detections, and we are grouping our detections by the host name over a 5-minute window. In the outcome section, we are generating a count of the number of events within each detection, as well as an array of the distinct values for target process file full path, since this is the field we will be using with our regex reference list. When we test our initial rule, we can see that we have 37 detections, and we can see that the target process file full path has a directory folder structure associated with each process. Let's open our list manager and take a look at our reference list called lolbin_regex. Lolbin is short for living off the land binaries. This isn't an exhaustive list, but there are some common tools that are either included on a Windows system or are utilities with very legitimate purposes that are often abused by adversaries who find them on the victim system. Because we can't always predict where some of these files may reside on a system, we can use regex reference lists and include the file names in a list, set the syntax type for the list to be regex, and then use it in our rule. Let's do that now. Here we've added a line to our rule that is looking in that target process file full path for regex values for our lolbin regex list. Now, when we test our rule, we will see that we have 7 detections. This is pretty good, but what if the target process file full path are mixed case or all caps? If we look at our list, we can see that all of our items in the list are lowercase, and in our initial rule execution, values like SQLcommand.exe were returned, but with that value in lowercase in our list, it was not found. This is because we are searching in a case-sensitive manner. If we wanted to set aside case sensitivity, we could prepend $I close parenthesis to SQLcommand.exe, which is how RE2 denotes case insensitivity. When we test our rule now, we have 11 detections, and we can see SQLcommand.exe, despite it being all caps, matching our criteria too. While this is one way to handle upper and lowercase characters, it isn't the only way. In fact, in our next video, we're going to introduce another function that does not require us to add $I close parenthesis to every item on our list. How's that for a cliffhanger? Today we demonstrated how we can compare multiple values in a single statement using regex matching and how we do not need the same level of precision as we do in a string reference list. Regex reference lists use RE2 and follow the same general syntax as other reference lists, except that the term regex is inserted after the in operator. Regex reference lists are very handy when working with files, commands, and folders that can be variable, as well as domains and other terms that we need to find a portion of the field. Reference lists can also easily find multiple values within a field without writing a large OR statement, and can be used in search, making these reference lists nice without making these reference lists. Just don't forget that if you have values that are all upper, lower, or mixed case, that you have a way to handle this variability. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to use CIDR reference lists in our YARA-L rules. CIDR reference lists build on top of the same concepts we covered in string reference lists, but have a more specific purpose. That purpose is to identify blocks of IP addresses based on CIDR notation rather than individual IP addresses. From a syntax perspective, little changes. We specify in our events section the UDM field name followed by in, CIDR, the %sign, and the reference list name. The reference list needs to be set to a syntax type of CIDR as well, and is done within the list manager. CIDR notation is supported for both IPv4 and IPv6 within a reference list. We're going to start by using our rule that detects core-light network connections that originate outside our defined net block of 10.128.0.0/24 and connect into it. We are excluding ICMP events and are grouping our detections by the principal IP address over a 30-minute window. In the outcome section, we are generating a count of the number of events within each detection to determine how many events are occurring within our match window. When we test our rule, we can see we have 73 detections, with a number of detections having numerous connection events associated with these external IP addresses. Let's look at how we could use a CIDR reference list to help us in our rule. Perhaps we've been running this type of rule for a while, and we've been researching these different IP addresses and determining that anything coming from the specific net block is nothing but trouble. In our example, the IP block of interest is 4579.0.0/16. While we could use our network function net IP in range CIDR and keep appending OR statements as we find more suspicious net blocks, this approach could be difficult to maintain and can't be reused within other rules. Using a CIDR reference list provides us a way to work with these net blocks. Let's take a look at our reference list called Suspicious IP CIDR Blocks. Here we can see a few different net blocks in the list. Notice at the top of the list, the syntax type is set to CIDR. If we created a list and used the wrong syntax, we can easily change it here. We just need to ensure we adjust our rule syntax accordingly as well. Because 4579.0.0/16 is of interest, we're going to detect on these events. Notice when we test our rule, we get 8 detections, all of which fit the net block of 4579.0.0/16. However, perhaps we continue our investigation of these IP addresses and realize that the net block has legitimate traffic in it, but the 45.79.160.0/24 and 4579.168.0/24 are really the net blocks of interest. We can modify our list to focus just on those net blocks, and when we test, we return 3 detections. Much like the string reference list, if we wanted to set up a list and say detect anything that is not on the list, we could do this as well by prepending not to our reference list criteria, like this. Now we get 70 detections, that is, everything that does not match the list. CIDR reference lists can be used to define internal network ranges, partner net blocks, and the like, and then reused in rules and search to easily identify unexpected network traffic. During our demonstration, we highlighted how we can use a CIDR reference list to detect IP addresses with a broader network block without having to specify every IP address in a range or using a large OR statement. The syntax for this is UDM field followed by in, CIDR, a %, and the list name. This syntax can also be used in search, and these reference lists can be reused in multiple rules, making them nice and portable. CIDR reference lists can be used for both IPv4 and IPv6 lists, depending upon your needs. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Google SecOps. I'm John Stoner, and today we're going to introduce another regular expression function. This one allows us to capture strings within fields that can be used elsewhere in our searches and YARA-L rules. re.recapture provides us a way to extract a portion of a value within a field and compare that portion to another value or write the captured value to a placeholder or outcome variable that can be used elsewhere. The syntax for re.recapture will generally be a field name followed by the expression that we are trying to match, and within that expression there will be a parenthesis that will denote what is being captured. For those not very familiar with this, don't worry, we'll walk through an example. Like other functions, the capture value can be nested and used with other functions. Let's take a look at this in action. Our example will look at process launch events, and we will group our detections by principal hostname over a 5-minute window. We will start by using the re.regex command in the target process command line field, and we'll look through the folder structure to find who am I before .exe. By the way, I use Gemini to generate the RE2 here, so don't feel like you need to be a regex ninja or anything. In the outcome section, we are outputting everything after the last folder to the command line outcome variable. When we test our rule, we can see who am I commands, but we still maintain the command switches in the output. That's one example of using re.recapture. Here's another. This time we are working with PowerShell data, and we have encoded PowerShell in our command lines. Let's separate the encoded PowerShell from the rest of the command line. We have a few lines using re.regex to focus on a subset of events, and then we have a placeholder variable called encoded value that we are going to use when we find values within the target process command line field that matches our regex. These values will contain -enc or ec or -en or -encoded command, followed by some non-word characters, and then capture everything after that that is non-white space. I'm sure folks can tighten this regex up further as needed. Anyway, we can take that placeholder variable, encoded value, and use it in the outcome section with the aggregate function array_distinct to output those values within our detection. When we test our detection, we can see our outcome variable with the encoded PowerShell in it. Notice how in our first example, we did the capture within the outcome variable as a nested function, and in the second example, we used a placeholder variable in the events section for the capture, and then outputted it in the outcome section. Both methods will work. It's really a question if you intend to do any additional manipulation on the values in the events section before outputting it. I'm sure you're looking at this and thinking, great, I have a field with encoded PowerShell. Now what? Well, perhaps you could run some automation on that value. Copy and paste it into your favorite decoding tool. I like CyberChef. Or you can check back next time where we'll use another function called strings.base64_decode to see the next step of our journey. As you can see, re.recapture allows us to capture a portion of a value that can be used for comparison or applied elsewhere in our rule or search. The syntax contains both the field and the regex expression, and remember that parentheses are used to capture the portion of the string you want to write to a variable or compare it to another string. Finally, these values can be used elsewhere once captured, or we can nest re.recapture with other functions. In fact, in our next video, we'll do just that. If you want to learn more about Google SecOps, check out my blog series called New to Google SecOps for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at secopscommunity.com. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the Adoption Engineering team at Google Cloud, and today we're going to introduce outcome variables and how they are used in a YARA-L rule. In previous videos, we covered the meta, events, match, and condition sections. Today we will introduce a new section called outcome. Along with this new section, we are going to introduce a new variable called outcome to go along with the event, match, and placeholder variables we previously discussed. The outcome section provides context to detections as well as the ability to perform aggregation functions of events that make up a detection. Outcome variables can be leveraged directly within Chronicle, but can also be helpful when integrating with ticketing systems and other integrations. These variables can be used to store descriptors like risk scores, MITRE attack techniques and IDs, calculated values, and lists of values when multiple events are part of a rule, and much more. The syntax for creating an outcome variable at its most basic level is the name of the variable with a $ in front of it, equals event variable.udm field name. Placeholder variables can be used in place of a UDM field name as well. If you want to go ahead and pass a string constant in, just enclose it in quotes. Outcome variables are not limited to a single event value and constant. In fact, we can use outcome variables to return an array of values from multiple events in a single detection or generate a calculated value. We won't get into those in this video, but as we start looking at multiple event rules as well as repeated fields, we will explore these concepts further. While we can leverage outcome variables and conditions, nothing else about our rule changes. So if you already have built rules using meta, events, match, and condition sections, adding an outcome section and additional fields don't require much more. Because this is the first time we are discussing the outcome section, we're going to start with the basics and build from there. Let's start with our rule whoami_execution, which is a very basic rule looking for process launches with the command line of whoami. Here we can see the results from our test rule. Maybe we want to provide some additional context for our detection, including a risk score of 10, the MITRE attack technique of system owner user discovery, and the host name of the system where this event was detected. To do this, we would define an outcome variable for each, followed by an equal sign, and then the constant or field name. Notice that the risk score is not enclosed in quotes as it is a numeric field. The attack technique does have quotes around it as it is a string, and the host name variable has the full UDM name, including the event variable. It's also worth pointing out that unlike placeholder variables, outcome variables must come first in the syntax. Let's go ahead and test our rule. In our results, not only can we add UDM fields to our detection view, but we can also add our outcome variables. If we add our 3 new fields, we can see them in the context of the detection. Now, you might be thinking, okay, adding a risk score and the attack technique to a single event field, I understand why we are adding them for additional context. But why do I add the additional field like host name when it's already in the UDM field? This goes back to the question, what are you going to do with your detections? If you're going to be integrating with a third-party tool, having key values like impacted system or user, as well as other descriptor fields like hashes, command lines, and IP addresses will be important. But the other benefit within Chronicle is being able to visualize these entities within the alert graph, like this. Here is an alert from a similar detection where we have added outcome variables for the hash, user, and asset values. While this is a simple detection, being able to visualize the associated entities to detection alerts is powerful, all because we're using outcome variables. I realize that showing the alert graph is likely to create more questions, but my point in doing this is to highlight that the use of outcome variables can be impactful. Outcomes add a new section to our rules, and with it comes the ability to add context to our detections. This context is created using syntax of $outcome variable name equals a field or constant. Remember, don't forget strings are enclosed in quotes, and while we didn't cover it today, outcome variables also provide a method to aggregate values and perform calculations, which will become very important when we start looking at multi-event rules. Outcomes can be helpful both in Chronicle as well as providing information about our detections to third-party systems, so adding outcomes can be quite valuable to your security operations team. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the adoption engineering team at Google Cloud, and today we are going to tackle risk score, conditional logic, and mathematical operators, all in the context of the outcome section in YARA-L. I hope we aren't biting off too much in this video, but let's give it our best shot. While we are going to apply the concepts of conditional logic and mathematical operations to a risk score today, it's important to understand that conditional logic, also known as if-then-else statements, and mathematical operators are not limited to calculating risk score. However, risk score was the first outcome variable created in Chronicle. It is considered a special variable as its value, when created in a rule, is represented in an alert queue as a numeric that analysts can use. The concepts of conditional logic are the same no matter if this is a single event rule or a rule with multiple events. However, the implementation will depend on a couple of factors. Specifically, is the field a repeated field? That is, can it have more than one value? And is the rule using a single event for the detection, or is it using multiple events? To illustrate this, let's take a look at a rule that detects admin shares. In our first example, we are looking for process launch events that meet a specific set of criteria in the target process command line field. Here we can see a version of the rule with its results. We could add a risk score using conditional logic here by adding an outcome variable like this. Risk score equals if process principal user department equals information technology, then 20, then 10, else 20. But wait a second, we're getting a syntax error. Why is that? When we click on the syntax checker, we can see that repeated fields require aggregation. Yes, even for single event rules with no match. What if we decided to use some other criteria for a non-repeated field, like principal user title? In that case, we'd have risk score equals if process principal user title equals intern 50, otherwise else 20. Notice our rule syntax is good, and when we test it, we can see that 4 detections have a risk score of 50 as the title of the user is intern, whereas the other titles are assigned a risk score of 20. While basing risk score on a user's title may not be ideal, hopefully you get the idea. For example 2, let's circle back to the repeated fields. To use them in a rule based on a single event, we need to prepend an aggregation function to the conditional logic. Let's change our risk score to look at the repeated field department, but this time let's prepend max to our expression. Risk score equals max if process principal user department equals information technology 20, else 50. When we test our rule, we can see that detections from the users not in the IT department will have a risk score of 50, but the IT staff will only have a risk score of 20. Which brings us to example 3. Our analysts probably don't want to have all of these detections individually because many of them are occurring within the same time frame, just from different data sets. Let's add a match section and group by hostname over 5 minutes. Notice how the same outcome variable with the max function works here because we are already aggregating the repeated value. Which leads us to example 4, our final one of this video. Let's add a mathematical operator to our risk score and use both the department and title to build the risk score. So here we have risk score equals max if process principal user department equals information technology, then 20, else 50, plus the max if process principal user title equals, or in this case contains intern, no case, then 5. As mentioned throughout our videos relating to outcome, all UDM fields that are part of the multi-event rule need to have an aggregate function associated with it. So our condition logic for the title also needs to be prepended by an aggregate function. Here we are getting a max value based on the department of the user and then adding to it a value of 5 if the title of the user contains intern. If you do not specify an else, the expression is still valid, it just won't do an else. Notice that the conditional logic can accept expressions including string matches and regex as well as the no case modifier. When our test rule completes, we can see that the risk score has been updated to meet our new criteria. Wow, that was a lot. We covered a bunch of concepts here, and if you aren't quite sure about all of them, don't worry. We'll continue to use outcomes and build on these concepts further, so this won't be the last time you see this. Just remember that the risk score is a reserved variable name that can be found in the alerts queue. Conditional logic can also be used throughout our outcomes, not just in risk score. It is set up as if field operator value, then X, else Y. Finally, mathematical operators including addition, subtraction, multiplication, division, and modulus can be used throughout the outcome section. There are some additional uses for mathematical operators, but they're beyond the scope of this video, so keep an eye out for them. Finally, don't forget that the aggregate functions are needed when working with multiple events in a rule or when repeated fields are being used, even in a single event rule. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the adoption engineering team at Google Cloud, and today we're going to look at using aggregate functions max, min, and sum within the outcome section in YARA-L. We're going to cover 3 aggregation functions that are used with integer and float fields in the outcome section, min, max, and sum. Remember, it's important to understand that when working with multiple events in a rule, that all outcome variables that contain UDM fields must have an aggregation associated with them. The general syntax we will use is the outcome variable equals min or max or sum, followed by the UDM field or a placeholder variable inside parentheses. There are not a lot of integer or float fields in UDM compared to string fields. So where min, max, and sum really shine is when used in conjunction with conditional logic and mathematical operations. This video will focus on how we can use these aggregation functions with UDM fields, but future videos will use these functions with conditional logic and mathematical operations. So think of this as building the foundation. To demonstrate the basic application of the aggregate functions for min, max, and sum, we're going to apply them to a network-centric rule. And as a bonus, once we use these functions in our outcomes, we will demonstrate how they can be used with the condition section to trigger a detection. The rule that we're starting with is looking for normal connection events coming from Zeek that have a received byte count that is greater than 0. We are grouping them by the host name over a 30-minute window. Everything we've talked about so far is really just gathering data of a certain type. In fact, if you look at the test rule I've run against this criteria, we just have a bunch of network traffic broken up by hostname every 30 minutes. But what if we wanted to aggregate our bytes received and view those values by the sum, the max, and the minimum bytes received? We could do that by using the outcome variables. What would we be grouping the sum, the min, and the max on? The match variable over the window, in this case, hostname over 30 minutes. Let's add these 3 variables to our outcomes section. When we test our rule and add the fields to our view, we can see the largest, smallest, and totals at the detection level. And if we expand the detection, we can also see the values at the event level for the networked receive bytes, which is the value we drew from to perform these calculations. Having some extra metrics for our analysts to see is nice, but we have a bit of an issue because of the number of the detections here are likely normal traffic. After all, these are normal Zeek connection events. But check this out. We can take outcome variables and add them to our condition section. Let's take our total bytes received outcome variable and add it to our condition section and append greater than 1 million to it. Okay, yeah, my byte values are a little on the low side here, but we are focusing on the concepts at the moment. Notice how the number of detections we have shrank. If we wanted to take another metric, like largest bytes received is less than 8,000, we could add that to our condition with another AND statement and further shrink our detections. Basically, what we have done is collect data, group it in our event and match sections, generate a set of calculations in the outcome section, and in this case, with min, max, and sum, and then apply these calculations to our detection logic in the condition section. We didn't cover it today, but the use of the outcome variables in conditions extends beyond just an integer like we covered. But this gives you an idea of what is possible. Min, max, and sum provide additional aggregate functions that can be used in the outcome section, but they are limited to float and integer fields. Don't forget that all event values must be aggregated in rules that contain multiple values. These aggregate functions follow a common syntax. The outcome variable equals the aggregate function, like sum, followed by parentheses with either the UDM event field with the event variable in front of it, or a placeholder variable inside of it. As we demonstrated, we can use outcome variables in our conditions to narrow our result set, but there is more to be unlocked with these three aggregate functions when used with conditional logic and mathematical operators. Which wraps this video up a bit like the end of a season cliffhanger. The good news is we will come back shortly to discuss these topics further. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections at our GitHub site and are continually adding more. And don't forget to engage the security community at googlecloudcommunity.com. Thanks. Welcome to Getting to Know Chronicle. I'm John Stoner, a member of the adoption engineering team at Google Cloud, and today we're going to start adding the outcome section to our multi-event rules and introduce aggregation, specifically counts, to our YARA-L rule. When we introduced outcomes, we used it with a single event rule. During that video, we mentioned that outcome variables could contain lists of values or calculated fields, but with a single event rule, there isn't much to list or calculate. With multi-event rules, we have more to work with. Today, we will cover two aggregation functions that can be used within the outcome section, count and count distinct. There are a number of other functions and we will get to them, but for this video, we will focus on these two. It's important to understand that when working with multiple events in a rule, that all outcome variables that contain UDM fields must have an aggregation associated with them. The syntax we will use is the outcome variable equals count or count distinct, followed by the UDM field or a placeholder variable inside parentheses. Finally, it's worth pointing out that any constants that you add to your outcome section do not require an aggregation function in front of them. You will see this in our video, but think of it this way. The constant is describing the entire detection, not a single UDM event. Therefore, we don't need to aggregate the values. With that brief overview, we're going to apply our outcome section to a password spray rule. Let's take a look at our current rule. The current rule is looking for Microsoft user login events with a block action, as you can see in the events section. We are grouping our detections by the match variable hostname over a 30-minute window, and we have a condition that says we need to have more than 10 unique user IDs within that window to trigger. So far, so good? Now, let's add some additional information to our detection. Much like our single event rule detection in our previous video, let's add a risk score of 65 and a MITRE ATT&CK technique of brute force password spraying. Notice that neither of these have an aggregation because they're both constants that describe the entire detection. Now, let's add 2 additional outcome variables. Even though we know that we want to detect when there are more than 10 unique users in our match window, let's get a count of the distinct user IDs in this detection, and while we're at it, let's get a count of the number of events that match our criteria for this spray. Notice in our 2 count aggregations that one is using a placeholder variable that we defined in the event section, and the other is using the full UDM field name. Either is valid, so use whichever one you'd like. When we test our rule, we will see that we get a few detections, and then by clicking on the columns button, we can add our 4 outcome fields to our results. The 2 outcome fields with the constants are as we define them, and with our 2 new outcome variables, we can see the unique number of users in our detection, as well as the number of events that matched our criteria as well. Count and count distinct are just 2 of the aggregate functions that can be used in the outcome section. Remember, all event values must be aggregated in rules that contain multiple values. To use these aggregate functions, they follow a common syntax. The outcome variable equals the aggregate function, like count, followed by parentheses with either the UDM event with the event variable in it, or a placeholder variable. Finally, constants do not require an aggregate function, even in multi-event rules. If you want to learn more about Chronicle, check out my blog series called New to Chronicle for more handy tips. We have a number of community YARA-L detections in our GitHub site and are continually adding more. And don't forget to engage the security community at googlecloudcommunity.com. Thanks.